imagine flying through a darkness that has no end, where even light itself loses its meaning and time ceases to exist. Do you feel that infinite emptiness all around you, which is paradoxically full of secrets waiting to be revealed, perhaps, in a quiet moment while gazing at the star-studded sky? You have asked yourself what actually lies out there, beyond the boundaries of everything we know, beyond the last planets, beyond the billions of stars, beyond the galaxies themselves. What is behind it all? And what if what awaits there changes everything we have ever thought about our place in the universe? Can we even comprehend what it would mean if the universe truly had an end? This journey to the edge of perception begins not in the distant cosmos, but right here, in our own cosmic backyard, as we methodically push the boundaries of what we call home, our solar system. This small island of light and order in the vast cosmic ocean begins with the sun. Our star, a huge churning ball of hot plasma, is the gravitational anchor of our system, containing over 99.8% of its total mass. 8 planets orbit this stellar furnace, each with its own unique story and character, a family of worlds born from the same swirling cloud of gas and dust, from scorching Mercury's a world of fire and ice to the distant, frigid majesty of Neptune. Each planet is a unique world, a testament to the diverse outcomes of planetary formation. Beyond the orbit of Neptune lies a vast, icy frontier known as the Kuiper Belt, a donut-shaped region of space teeming with dwarf planets, comets, and other remnants from the solar system's birth. This is where Pluto resides, once considered the 9th planet but now reclassified as the king of the Kuiper Belt objects. This region is home to countless similar bodies, frozen time capsules that preserve the chemical and physical conditions of the early solar system. But where does the influence of our sun truly end? Where is the boundary that separates our solar system from the great expanse of interstellar space? The answer lies at the heliopause, a theoretical boundary where the solar wind, a constant stream of charged particles flowing outward from the sun at supersonic speeds, collides with the interstellar medium and slows to a subsonic crawl. It is a dynamic, invisible border, like the bow shock of a boat moving through water, the place where the sun's sphere of influence gives way to the galaxies. In 2012, NASA's Voyager 1 probe, a relic of the 1970s, became the first human-made object to cross the boundary and enter interstellar space. Followed 6 years later by its sister probe, Voyager 2, these 2 intrepid explorers, now tens of billions of kilometers from home, became our first messengers into the unknown, our first direct taste of the space between the stars. The heliopause is located at a fluctuating distance of approximately 120 astronomical units from the Sun. 1 astronomical unit is the average distance between the Earth and the Sun, about 149 million kilometers. This means the edge of the Sun's direct influence is about 18 billion kilometers away. Imagine traveling at the speed of light, 300,000 kilometers per second, even at this unimaginable velocity. The journey from the Sun to the heliopause would take you more than 16 hours, and that is just the first or tentative step on our journey beyond the known. Beyond the heliopause, in the dark and unimaginably cold space, lies one of the most mysterious and hypothetical regions of our solar system, the Oort cloud. Imagine a vast, spherical shell of icy bodies, a colossal cocoon surrounding our entire system, extending out to the very limits of the Sun's gravitational grasp. This structure was first theorized by the Dutch astronomer Jan Oort in 1950 as a way to explain the origin of long-period comets, those that visit the inner parts of the solar system only once every thousands or even millions of years. He proposed that there must be a vast, distant reservoir of these icy bodies, and that they are occasionally perturbed from their stable orbits and sent on a long journey toward the Sun. While no object has ever been directly observed in the Oort cloud, the evidence for its existence from the orbits of these comets is compelling. While the Kuiper Belt is a relatively flat, donut-shaped region located just beyond Neptune, from about 30 to 50 astronomical units from the Sun, the Oort cloud is a much larger spherical structure. Its inner boundary is thought to lie at approximately 1,000 astronomical units, while its outer edge could extend to a staggering 100,000 astronomical units. That is almost a quarter of the way to the nearest star, Proxima Centauri. In this distant, frigid realm, the Sun would appear as just a very bright star, and its gravitational influence would be incredibly weak. Objects in the Oort cloud are thus easily influenced by the gravity of passing stars, giant molecular clouds, or even the tidal forces of the Milky Way galaxy itself. These objects are true borderlanders, technically part of our solar system but already feeling the pull of the wider galactic environment. Every long-period comet streaks across our night sky is a messenger from this distant, unseen world, a pristine sample of the primordial material from which our solar system was formed, bringing us information about the conditions in the early days of its history. Some scientists speculate that similar Oort-like clouds surround other star systems. Perhaps, in the vast spaces between the stars, there are places where these clouds overlap and almost touch, creating a kind of cosmic bridge, a network of icy bodies connecting neighbouring star systems. When we finally leave the outermost tenuous boundaries of our solar system, we step into the region known as interstellar space. This space is not the perfect vacuum of popular imagination. It is filled with a diffuse, tenuous substance that astronomers call the interstellar medium, a sparse mixture of gas, dust, plasma, and radiation that fills the vast voids between the stars. The density of the interstellar medium is extremely low, on average just 1 atom per cubic centimetre. For comparison, the air we breathe has about 10 to the power of 19 molecules per cubic centimetre. The vacuum in interstellar space is far better than any we can achieve in a laboratory on Earth. Yet, on the immense scales of the galaxy, this seemingly insignificant matter adds up to approximately 10 to 15% of the total visible mass in our galaxy. The interstellar medium is composed of about 99% gas, mostly hydrogen and helium, and 1% dust, tiny solid particles of silicates, carbon, and ice, typically smaller than the particles in smoke. This dust plays a crucial role in the life cycle of the galaxy. It absorbs and scatters starlight, which causes distant stars to appear dimmer and redder to us than they actually are, a phenomenon known as interstellar reddening and extinction. It also provides the raw material and the catalytic surfaces on which new stars and planetary systems form. Interstellar space is also permeated by magnetic fields and is constantly bombarded by cosmic rays high-energy particles, mostly protons and atomic nuclei that travel through the universe at speeds approaching the speed of light. This radiation comes from various violent cosmic sources, including supernova explosions, active galactic nuclei, and solar flares from our own sun and other stars. The Voyager probes, now travelling through this unexplored territory, are providing scientists with invaluable direct data about the conditions in the local interstellar medium. They have found that the space just outside our heliosphere is warmer and denser than expected, and that the interstellar magnetic field is surprisingly strong and has a different orientation than the one generated by our Sun. The interstellar medium is not static or uniform. It is a dynamic and turbulent environment, shaped by the life and death of stars, super bubbles huge, hot cavities carved out by the powerful stellar winds from massive stars, and the shockwaves from multiple supernova explosions can sweep up and compress the surrounding gas, triggering new waves of star formation. This creates a complex, ever-changing structure, a kind of cosmic foam or labyrinth through which everything that moves between the stars must travel. Sometimes, visitors from these distant regions grace our own solar system with their presence. In 2017, astronomers observed Oumuamua, a strange cigar-shaped object that was the first interstellar object detected passing through our solar system. Its trajectory clearly indicated that it had come from another star system. 2 years later, a second interstellar visitor, the comet Borisov, was discovered. These objects are precious messengers from other star systems, providing us with our first direct samples of the material from which other worlds are made. As we continue our journey outward, we would leave the Sun's faint gravitational influence behind and enter the domain of other stars. As we travel further from the edge of our solar system, the first stellar destination we would encounter is Proxima Centauri, a small dim red dwarf star that is part of the triple star system Alpha Centauri. It is located at a distance of 4.2 light-years, a journey that would take light over 4 years to complete. For a spacecraft like the Voyager probes, the journey would take approximately 70,000 years. Proxima Centauri is a much different star than our Sun. It is a tiny, cool red dwarf, with only about 12% the mass and a tiny fraction of the luminosity of our star. It radiates only about 1,000th of the Sun's energy, mostly in the infrared part of the spectrum. Yet, this faint star is home to at least one known planet, Proxima Centauri b, a rocky world only slightly more massive than Earth that orbits in the star's habitable zone, the region where temperatures could allow for the existence of liquid water on its surface. This exoplanet is one of the closest and most tantalizing places where we could search for signs of life beyond our solar system, though the intense stellar flares from its active red dwarf parent star pose a significant challenge to its potential habitability. The other two stars in the system, Alpha Centauri A and Alpha Centauri B, are much more like our Sun. They form a tight binary pair orbiting a common center of gravity with a period of approximately 80 years. Such binary and multiple star systems are much more common in the universe than solitary stars like our Sun. A little further away, approximately 8.6 light-years from us, is Sirius, the brightest star in our night sky. It, too, is a binary system, composed of a brilliant main sequence star, Sirius A, which is about twice as massive and 25 times more luminous than our Sun, and a faint white dwarf companion, Sirius B. Sirius B is the remnant of a once massive star that has exhausted its nuclear fuel, a dense, Earth-sized ember that is the first white dwarf ever to be discovered. Within a radius of 20 light-years from the Sun, there are approximately 60 known star systems. The vast majority of these are faint, cool red dwarfs, the smallest and most common type of star in the galaxy. These stars are so dim that none of them are visible to the naked eye. Even though some are relatively close neighbours, astronomers have discovered planets orbiting many of these nearby stars. Tau Ceti, a star very similar to our Sun located just 12 light-years away, has at least 4 known planets, Epsilon Eridani, at a distance of 10.5 light-years, has at least 1 confirmed planet and an extensive asteroid belt. What this growing census of our local stellar neighbourhood tells us is that planets are the rule, not the exception. It is likely that almost every star we see in the night sky has its own planetary system. The universe is full of worlds, some similar to Earth, others completely different from anything we can imagine. A quiet night under the stars will never be the same once we realize that each of those distant points of light could be home to countless other worlds, each with its own story, its own history, and its own potential. Our solar system is just a tiny, almost insignificant point of light in a vast, swirling disk of stars that we call the Milky Way galaxy. This galaxy, our cosmic home, is a colossal structure, containing somewhere between 100 and 400 billion stars, along with vast clouds of gas and dust. Its diameter is estimated to be about 100,000 light-years. This means that a beam of light, travelling at the ultimate cosmic speed limit of 300,000 kilometers per second, would need 100,000 years to journey from one end of the galaxy to the other. Our Sun is located in one of the galaxy's spiral arms, a minor spur called the Orion Cygnus Arm, about 26,000 light-years from the galactic centre. We are neither at the heart of the action nor on the absolute periphery, but somewhere in the galactic suburbs, a relatively quiet and stable region that may have been conducive to the long-term evolution of life. The Milky Way is a barred spiral galaxy. It has a central bar-shaped structure composed of old, reddish stars, from which several major spiral arms extend, winding their way outward. These spiral arms are not solid structures, but rather density waves, regions where the gas, dust, and stars are slightly more compressed. They are the primary sites of new star formation, and so they are illuminated by the brilliant, blue light of young, massive stars. The spiral arms are like a cosmic traffic jam. Stars and gas clouds move into and out of these regions, slowing down as they enter the dense arm and speeding up as they leave. The arms themselves are a persistent pattern that rotates more slowly than the individual stars. At the very center of our galaxy, shrouded from our view in visible light by thick clouds of interstellar dust, lies a supermassive black hole named Sagittarius A star. This cosmic behemoth has a mass equivalent to about 4 million suns, all compressed into a region smaller than the orbit of Mercury. It is the gravitational anchor of our galaxy, and a dense cluster of stars orbits this black hole at incredible speeds, some reaching up to 5,000 kilometers per second. Our galaxy is also surrounded by a vast spherical halo, a region that extends far beyond the visible disk and contains old stars, ancient globular clusters, and a huge, invisible component of dark matter. This halo contains the bulk of the galaxy's mass and is responsible for its overall gravitational pull. The globular clusters found in the halo are dense, spherical swarms of hundreds of thousands of very old stars, some of which are among the oldest objects in the galaxy, witnesses to its formation more than 13 billion years ago. The Milky Way is not a static formation, it is a dynamic, evolving system. It rotates, with stars and gas orbiting the galactic center. Our Sun, along with its family of planets, is moving at a speed of about 220 kilometers per second, completing one full orbit of the galactic center in approximately 225 to 250 million years. This period is sometimes called a galactic year. Since our solar system formed about 4.6 billion years ago, it has completed about 20 such journeys around the galactic core. A look at the night sky on a clear, moonless night, far from the light pollution of our cities, reveals a faint, shimmering, milky band of light that stretches from horizon to horizon. This is a view of our own galactic disk from our vantage point within it. We are looking into the plane of the galaxy, at the combined light of billions of distant, unresolved stars, their individual glimmers merging into this ethereal celestial river. It is from this view that our galaxy got its name, which reminded the ancient Greeks of spilled milk. The Milky Way is not a solitary island in the universe. It is one of the two largest members of a gravitationally bound collection of galaxies known as the Local Group. This group, which spans a diameter of approximately 10 million light-years, contains over 50 known galaxies of various shapes and sizes. The dominant members of this cosmic neighborhood are two giant spiral galaxies, our Milky Way and the Andromeda Galaxy, also known as Messier 31. Andromeda is slightly larger and more massive than our galaxy, with a diameter of about 140,000 light-years and containing an estimated 1 trillion stars. It is located at a distance of 2.5 million light-years and is the most distant object that can be seen with the naked eye on a dark night, a faint, fuzzy patch of light that is actually an entire other galaxy. The third largest member of the Local Group is the Triangulum Galaxy, another spiral galaxy, but considerably smaller than its two larger neighbours. The other members of the group are mostly small, irregularly shaped dwarf galaxies, which orbit the three main galaxies like satellites around planets. The Milky Way has at least 14 known satellite galaxies, with the most famous being the Large and Small Magellanic Clouds, two irregular dwarf galaxies that are prominent features in the night sky of the southern hemisphere. These satellite galaxies are in a constant gravitational dance with the Milky Way, and some are in the process of being tidally disrupted and absorbed by our larger galaxy. The galaxies in the Local Group are not static. They are moving relative to each other under the influence of their mutual gravity. The most dramatic example of this is the motion of the Andromeda Galaxy, which is heading directly towards our Milky Way at a speed of about 110 kilometers per second, in about 4.5 billion years. These two galactic titans will begin a series of close encounters and eventually merge into one giant elliptical galaxy. This cosmic collision will not be as catastrophic as it sounds. The space between the stars in a galaxy is so vast that direct stellar collisions will be extremely rare. Instead, the two galaxies will pass through each other, their stars and planetary systems mixing under the influence of gravity, creating long, spectacular tidal tails of stars and gas that are pulled out into intergalactic space. After several such passes over hundreds of millions of years, they will settle down into a new, larger, and more spherically shaped galaxy, which some astronomers have already playfully named Milkomeda. The Local Group as a whole is not at rest, either. It is moving at a speed of about 600 kilometers per second towards an even larger structure, the Virgo supercluster. The study of the dynamics of the Local Group provides us with crucial information about the distribution of matter in our cosmic neighborhood, including the invisible dark matter, which dominates the mass of the group and governs its evolution. As we zoom out even further from our Local Group, we enter the realm of the truly colossal cosmic structures as superclusters of galaxies. These are enormous assemblages of matter, among the largest coherent structures in the known universe, containing thousands of galaxies that are gravitationally linked into intricate webs and filaments. Our own Local Group is just a small, outlying component of a vast structure known as the Local Supercluster, or the Virgo Supercluster. This gigantic collection of galaxies has a diameter of approximately 110 million light-years and contains at least 130 galactic groups and clusters, with a total of more than 1,200 known galaxies. At the heart of the Virgo supercluster lies the Virgo cluster, a huge, dense concentration of about 1,500 galaxies, dominated by the giant elliptical galaxy Messier 87. This cluster is so massive that its immense gravitational pull significantly influences the motion of all the surrounding galaxies, including our own local group. Astronomers have found that we are moving towards the centre of the Virgo cluster at a speed of several hundred kilometres per second. In 2014, a team of astronomers redefined our place in the cosmic hierarchy by discovering that the Virgo supercluster is itself just a small lobe of an even larger gravitational structure, which they named Laniakea, a Hawaiian word meaning immense heaven. Laniakea is a vast supercluster that spans an area of roughly 520 million light-years and contains approximately 100,000 galaxies, with a total mass equivalent to 100 quadrillion times the mass of our Sun. The boundaries between superclusters are not sharp, well-defined edges like the coastlines of continents on Earth. Instead, they are defined by the flow of galaxies. Galaxies within one supercluster tend to move, or flow, towards a common gravitational centre, a region known as a great attractor. Galaxies in neighbouring superclusters flow towards other centres of gravity. Laniakea is defined as the region of space where all the galaxies are flowing towards a single point, the Great Attractor, which is located in the direction of the constellation Centaurus and Hydra. Superclusters of galaxies are not randomly distributed in space. They are arranged along huge interconnected filaments or threads, and at the intersections of these filaments, we find the densest galaxy clusters. These filaments, in turn, surround gigantic, almost empty regions of space called cosmic voids. This arrangement gives the universe, on its largest scales, a structure that resembles a cosmic web or a giant, three-dimensional sponge. The largest known structures in the universe are these vast superclusters and filaments. The Hercules Corona Borealis Great Wall, for example, is a colossal filament of galaxies that has a diameter of approximately 10 billion light-years. It is such a huge object that light would need 10 billion years to travel from one end to the other, which is almost 3/4 of the age of the universe itself. The existence of such immense structures poses a challenge to some of our cosmological models. This cosmic web is not the result of chance. It is a direct consequence of the tiny, random quantum fluctuations that existed in the density of the very early universe. During the period of cosmic inflation, these microscopic fluctuations were stretched to cosmological scales. The regions that were slightly denser than average became the seeds for the future structure. Over billions of years, gravity amplified these initial irregularities. The denser regions attracted more and more matter, both dark matter and ordinary matter, pulling it away from the less dense regions. This process, known as gravitational instability, caused the matter in the universe to collapse into the intricate web-like pattern that we observe today. The filaments of the cosmic web are made of dark matter, which forms a kind of invisible skeleton or scaffolding along which the galaxies and intergalactic gas are arranged. These filaments act as cosmic highways, funneling matter towards the nodes of the web, where the largest and most massive galaxy clusters are located. Between the filaments are the cosmic voids, regions with an extremely low density of matter. These voids can have diameters of up to hundreds of millions of light-years, but they are not completely empty. They contain a very sparse, diffuse gas and a few isolated galaxies that have evolved there in relative isolation from the main cosmic structures. The existence of this web-like structure was first hinted at in the 1980s, when astronomers began to create the first three-dimensional maps of the distribution of galaxies. The famous survey known as the CFA Redshift Survey revealed the first evidence of this structure, including a huge filament of galaxies that was dubbed the Great Wall. Since then, much more extensive and detailed surveys have been conducted, such as the Sloan Digital Sky Survey, which has mapped the positions and distances of millions of galaxies. These surveys have confirmed that the universe indeed has a foam-like or web-like structure on the largest scales. Computer simulations of the universe's evolution, which are based on our current understanding of physics and take into account the influence of dark matter and dark energy, can reproduce this cosmic web with remarkable accuracy. This gives us great confidence that our basic understanding of how the universe evolved from a nearly perfectly smooth state shortly after the Big Bang to today's complex, fibrous structure is correct. The study of this large-scale structure provides us with crucial information about the composition and evolution of the universe, and every new map of the cosmos adds another piece to this fascinating cosmic puzzle. As we travel even further, to the very limits of our observational capabilities, we reach the edge of the observable universe. The observable universe is the region of space from which light has had enough time to reach us since the origin of the universe 13.8 billion years ago. It is, in effect, a cosmic horizon, a boundary beyond which we cannot see anything. Not because there is nothing there, but because the light from those more distant regions has not yet had time to reach us. The diameter of the observable universe is approximately 93 billion light-years. This may seem like a paradox. Given that the universe is only 13.8 billion years old, this apparent discrepancy is caused by the fact that the universe has been expanding during the time that the light has been travelling. The objects that emitted the light we observe today were much closer to us at the time of emission, but they have since been carried much farther away from us by the expansion of space. At the very edge of the observable universe, we are seeing the universe as it was shortly after the Big Bang. The oldest light we can observe is the cosmic microwave background, the fossil radiation that originated about 380,000 years after the Big Bang. At that time, the universe had cooled enough for electrons to combine with nuclei to form neutral atoms, a process called recombination, which allowed photons to travel freely through the universe for the first time. This cosmic microwave background is ubiquitous and comes to us from all directions of the sky. It is more in effect a snapshot of the infant universe, and it contains tiny fluctuations in temperature and density that were the seeds for all the structures we see today. The study of these fluctuations provides us with a wealth of information about the composition, geometry, and evolution of the universe. Beyond the cosmic microwave background is a period known as the Dark Ages, a time when there were no stars or galaxies in the universe yet. This period ended when the first stars and galaxies began to form, an era known as the Cosmic Dawn, which occurred somewhere between 100 million and 1 billion years after the Big Bang. The observable universe is estimated to contain approximately 2 trillion galaxies, each with hundreds of billions or even trillions of stars. This means that the observable universe contains more stars than there are grains of sand on all the beaches of Earth, and that is only the part we can see, what lies beyond the boundaries of our observable universe. The most likely and simplest answer is more universe, a universe that is very similar to the part we can see stretching on for a much greater distance, perhaps even infinitely. Our best cosmological theories suggest that the universe could be infinite, or at least vastly larger than the part we can observe. These distant regions are forever hidden from us. Their light will never reach Earth due to the continuous and accelerating expansion of the universe. They are beyond our cosmic event horizon, lost to us forever. What if our observable universe, with all its 2 trillion galaxies, its countless stars, and its untold number of planets, is just one bubble in an infinite ocean of other universes? This idea, known as the multiverse theory, is one of the most provocative, mind-bending, and controversial ideas in all of modern cosmology. There are several different versions of the multiverse theory, each arising from a different branch of modern physics. One of the most well-developed of these is the inflationary multiverse, which stems directly from the theory of cosmic inflation. Inflation proposes an extremely rapid accretion of the universe in the first fraction of a second after the Big Bang. In many models of inflation, this process is eternal. It may have stopped in our local region, creating our universe, but it continues in other, more distant regions, constantly spawning new bubble universes, each with its own Big Bang, its own history, and potentially its own unique set of physical laws and constants. Our universe would be just one bubble in a vast, eternally expanding cosmic foam. Another version of the multiverse comes from the strange rules of quantum mechanics and its many worlds interpretation. This theory, proposed as a solution to the measurement problem, suggests that every time a quantum event with multiple possible outcomes occurs, the universe itself splits into several parallel branches. In each branch, one of the possible outcomes is realized. This would mean that there is an infinite number of parallel universes, some almost identical to our own, others radically different, all existing simultaneously in a vast, abstract mathematical space. There would be a universe where you chose a different path in life, a universe where the dinosaurs never went extinct, and a universe where the laws of physics are subtly different. The idea of a multiverse, while it may seem like science fiction, could help to explain one of the deepest mysteries of modern cosmology, the so-called fine-tuning of the universe. The fundamental constants of nature in our universe, such as the strength of the four fundamental forces, the mass of the elementary particles, and the amount of dark energy, seem to be exquisitely and precisely set to the narrow range of values that allows for the existence of complex structures, including stars, planets, and life. If any of these constants were even slightly different, the universe would be a sterile and uninteresting place. In the context of a multiverse, this fine-tuning is not a mystery. If there is an infinite number of universes, each with a random set of physical laws and constants, then it is not surprising that we find ourselves living in one of the rare universes that is suitable for life. We are here simply because we could not be anywhere else. This is a form of the anthropic principle. Although the idea of a multiverse is fascinating and has a certain philosophical appeal, it is important to note that it is still a highly speculative theory that currently has no direct experimental evidence by their very nature. These other universes are likely to be forever beyond our ability to observe, which has led some critics to argue that the multiverse is not a scientific theory at all, as a scientific theory should be falsifiable. Nevertheless, some scientists believe that there could be indirect ways to test the idea. For example, if our bubble universe had once collided with another bubble universe in the distant past, it might have left a detectable signature, a kind of cosmic bruise in the temperature patterns of the cosmic microwave background. Scientists are actively searching for such anomalies, but so far without any convincing results. The idea of a multiverse has profound philosophical implications. If it is true, then our universe, however vast and majestic it may seem to us, is just an infinitesimal part of a much larger, and perhaps infinite, reality, and this forces us to completely rethink our place in the cosmos and the very nature of existence itself. To understand what might lie beyond the boundaries of our universe, we must first grapple with the nature of space and time itself. According to Einstein's general theory of relativity, space and time are not separate, independent entities, but are woven together into a single, unified, four-dimensional fabric called spacetime. This spacetime is not just a passive, empty stage on which the events of the universe unfold, but is a dynamic entity that is shaped and curved by the presence of matter and energy. A good analogy is to imagine spacetime as a huge, flexible rubber sheet. When you place a heavy object, like a star or a planet, on this sheet, it creates a depression or a warp in the fabric. Other objects then do not fall towards these massive bodies due to some mysterious attractive force called gravity, but rather they follow the curved paths created in spacetime, much like a marble rolling on a curved surface. In this view, gravity is not a force, but a manifestation of the geometry of spacetime itself. This is one of the deepest and most elegant insights of modern physics, and it completely changed our view of the nature of gravity. General relativity also predicts the existence of gravitational waves, ripples in the fabric of spacetime that are generated by accelerating massive objects, such as two black holes orbiting each other and merging. These waves propagate through the universe at the speed of light, carrying information about the most violent and energetic cosmic events. In 2016, these gravitational waves were first directly detected by the LIGO Observatory, an achievement that opened a completely new window onto the universe, allowing us to listen to the cosmos in a way that was previously impossible. Spacetime may also have an energy of its own, an idea known as vacuum energy. According to quantum field theory, even a perfectly empty space is not truly empty, but is filled with a sea of virtual particles that are constantly being created and annihilated. This roiling quantum foam gives the vacuum a non-zero energy, which could be related to the mysterious dark energy that is causing the accelerated expansion of the universe. On the very smallest scales, approaching the so-called Planck length, which is about 10 to the minus 35 meters, our classical concept of a smooth, continuous spacetime is expected to break down. At these scales, quantum effects should become dominant, and spacetime may have a granular or foam-like structure, constantly fluctuating and changing its topology. This quantum foam could be the fundamental substrate of reality, and some theories suggest that it could be the source of the creation of new universes in a multiverse scenario. If the universe is indeed a multiverse, what might the space between the individual universes look like? This is an extremely speculative question, as our current theories may not be applicable outside our own universe. Some models suggest that different universes could be separated by extra hidden dimensions, or could exist as branes floating in a higher dimensional bulk space. The nature of this metaspace is something that we can currently hardly even imagine. There is also the possibility that our universe itself contains gateways that could lead to other universes. Theoretical objects like wormholes, which are hypothetical tunnels through spacetime, could connect different and distant regions of our universe, or even different universes altogether. For now, however, these objects remain purely mathematical possibilities with no direct observational evidence. When astronomers study the motion of stars in galaxies or the motion of galaxies in clusters, they encounter a profound mystery. The stars and galaxies are moving as if they are under the influence of a much greater gravitational force than can be accounted for by all the visible matter. This discrepancy led to the hypothesis of the existence of dark matter, an invisible, mysterious substance that interacts with other matter primarily through the force of gravity. The idea of dark matter was first proposed in the 1930s by the Swiss-American astronomer Fritz Zwicky, who was studying the motion of galaxies in the Coma cluster. He found that the galaxies were moving so fast that the cluster should have been flying apart. Unless there was a huge amount of unseen mass providing the extra gravitational glue. Several decades later, the American astronomer Vera Rubin provided even more compelling evidence when she studied the rotation curves of spiral galaxies and found that the outer stars were orbiting just as fast as the inner ones, a clear violation of Newton's laws of gravity unless the galaxies were embedded in a vast halo of dark matter. Today's precise measurements indicate that dark matter makes up about 27% of the total mass-energy content of the universe, while ordinary or baryonic matter, from which stars, planets, and we ourselves are made, constitutes only about 5% the rest of the universe. About 68% is made up of an even more mysterious component. Dark energy, dark matter played a crucial role in the formation of structures in the universe. In the early universe, dark matter, which does not interact with light, was able to begin clumping together under its own gravity much earlier than ordinary matter. It formed a kind of cosmic scaffolding, a network of deep gravitational wells into which ordinary matter subsequently fell. These initial accumulations of dark matter were the seeds that later grew into the galaxies and large-scale structures that we observe today. Without dark matter, the universe would look completely different, with a much more uniform distribution of matter, and perhaps without the possibility for the complex structures needed for life to form. What exactly is this mysterious dark matter? This remains one of the greatest unsolved puzzles in all of modern physics. The leading theory is that it's composed of some kind of as-yet undiscovered subatomic particles that interact very weakly with ordinary matter, which is why they are so difficult to detect. These hypothetical particles, such as WIMPs or actions, would be passing through us and our planet all the time, almost without notice. Scientists around the world are conducting a variety of experiments to try to directly detect these elusive particles. These experiments are usually located deep underground, in mines or tunnels, to shield them from the constant rain of cosmic rays and other background radiation. They include large tanks filled with liquid noble gases, like xenon, or ultra-pure crystalline detectors, which are designed to register the rare event of a dark matter particle bumping into an atomic nucleus. Alternative theories suggest that dark matter may not exist at all, and that the observed anomalies in the motion of stars and galaxies can be explained by a modification of our laws of gravity over very large distances. However, these theories, such as Emma Indy, have had difficulty explaining some of the observational evidence that the dark matter theory elegantly explains, such as the properties of the cosmic microwave background and the behavior of colliding galaxy clusters. Whatever dark matter turns out to be, its study is crucial for our understanding of the fundamental nature of the universe and its evolution. It is a powerful reminder of how much we still do not know about the cosmos and how exciting the journey of discovery can be. Even more mysterious and enigmatic than dark matter is the phenomenon of dark energy, the invisible force that is causing the universe to expand at an ever-increasing rate. While dark matter manifests itself through its gravitational pull, which attracts matter and holds galaxies together, dark energy acts as a kind of cosmic repulsive force, pushing the large-scale structures in the universe away from each other. Its existence was first inferred in 1998, when two independent teams of astronomers were studying distant-type Ia supernovae. These cosmic explosions, which all have nearly the same intrinsic brightness, serve as excellent standard candles, allowing astronomers to accurately measure their distances. To the great surprise of the scientific community, the most distant supernovae were found to be fainter and therefore farther away than predicted by the cosmological models of the time. This indicated that the expansion of the universe was not slowing down due to the gravitational pull of matter, as had been long assumed, but was in fact accelerating. This groundbreaking discovery, which earned its pioneers the Nobel Prize in Physics in 2011, led to the hypothesis of dark energy as the driving force behind this cosmic acceleration. According to our best current measurements, dark energy makes up approximately 68% of the total mass energy content of the universe, making it the dominant component of the cosmos today. What exactly this dark energy is remains a subject of intense research and debate. The simplest and leading explanation is that it is the so-called cosmological constant, a fundamental and intrinsic property of space itself, which has a constant, unchanging energy density. This idea has its roots in Einstein's original equations of general relativity, where he introduced a similar constant as a way to achieve a stable and non-expanding universe, which was the prevailing cosmological view at the time. When Edwin Hubble later discovered that the universe is expanding, Einstein famously called the introduction of the cosmological constant his biggest blunder. The great irony is that current observation suggests that something very similar to this cosmological constant does indeed exist and plays a dominant role in the dynamics of the universe. Alternative explanations for dark energy include the idea of quintessence, a hypothetical dynamic field that permeates all of space and whose energy density can change over time. Depending on how this field evolves, the future of the universe could be very different. Another possibility is that our understanding of gravity on the very largest cosmic scales is incomplete and requires modification, but the most tantalizing, and also the most problematic, connection is with the energy of the quantum vacuum. Quantum field theory predicts that even empty space should be filled with a non-zero energy due to the constant creation and annihilation of virtual particles. This vacuum energy would have the same repulsive gravitational effect as a cosmological constant. The problem is that the theoretical calculations of the amount of this vacuum energy are wildly, catastrophically wrong, predicting a value that is about 120 orders of magnitude larger than what we observe. This is one of the biggest unsolved problems in physics. The future of the universe depends fundamentally on the nature of this mysterious dark energy. If it is a cosmological constant, then the accelerating expansion will continue forever. This would eventually lead to a scenario known as the Big Freeze, or the heat death of the universe. Galaxies outside our local group will recede from us until they disappear beyond our cosmic horizon. Star formation will eventually cease, and the existing stars will one by one burn out after trillions of years. The universe would be a dark, cold, and empty place, populated only by the dead remnants of stars and black holes. Even these would eventually evaporate through Hawking radiation, leaving behind only a sparse, diffuse gas of elementary particles approaching absolute zero. A more violent possibility is the Big Rip. And if the repulsive force of dark energy were to grow stronger over time, the expansion of the universe would continue to accelerate dramatically until it eventually tore apart all gravitationally bound structures, including galaxies, stars, planets, and finally, even atoms and their nuclei. Everything would be ripped apart into its fundamental constituents, scattered in an infinite, ever-expanding void. If dark energy were to change its character and become attractive, the universe could be heading for a big crunch, collapsing back in on itself in a fiery mirror image of the Big Bang. And some theories of quantum gravity suggest the possibility of a big bounce, where the universe goes through endless cycles of expansion and contraction. The study of dark energy is one of the most active and important areas of contemporary cosmology. Scientists are using increasingly sophisticated methods to measure the expansion of the universe with ever greater precision, hoping to reveal the true nature of this mysterious force that is shaping the ultimate destiny of our universe and defining the very boundaries of our cosmic future. To understand what might lie beyond the boundaries of our universe, we must also understand how the universe was created and how it acquired its present-day structure. One of the most important and successful concepts in this field is the theory of cosmic inflation, which describes a period of extremely rapid, exponential expansion of the universe in the first fraction of a second after the Big Bang. The theory of inflation was proposed in the early 1980s by the American physicist Alan Guth as a solution to several nagging problems of the standard Big Bang model. One of these was the horizon problem, the question of why the cosmic microwave background is so remarkably uniform in temperature across the entire sky, even though regions on opposite sides of the sky were too far apart to have ever exchanged heat and reached thermal equilibrium. Inflation solves this problem by assuming that the entire observable universe originated from a tiny, causally connected patch of space that was stretched to an enormous size during a brief period of hyperexpansion. According to this theory, at about 10 to the minus 36 seconds after the Big Bang, the universe underwent a phase of exponential expansion, during which its size increased by a factor of at least 10 to the power of 26 in an incredibly short time. It is like an object the size of a subatomic particle growing to the size of a galaxy in a fleeting instant. This dramatic expansion was driven by the energy of a special state of matter, a quantum field known as the inflaton field. At the end of the inflationary epoch, the energy of this field was converted into the particles of ordinary matter and radiation that we see today, in a process known as reheating, which essentially kick-started the hot, dense state of the standard Big Bang model. Inflation not only solves the horizon problem and the flatness problem, the question of why our universe is so geometrically flat, but it also provides a natural mechanism for the formation of structures in the universe. The tiny random quantum fluctuations that are always present on the smallest scales were stretched to macroscopic cosmological scales during inflation. These fluctuations became the seeds, the slight overdensities and underdensities, from which all future galaxies and large-scale structures grew through gravitational attraction. These primordial fluctuations left a distinct imprint in the temperature variations of the cosmic microwave background, which have been observed with incredible precision by satellites like Planck. The statistical properties of these fluctuations match the predictions of inflation remarkably well. There are different variants of inflationary theory, including the model of eternal inflation, which assumes that the process of inflation once started never completely ends. Instead, it continues in some regions of space while ending in others, like our own, creating a vast, ever-growing number of bubble universes. This would mean that our universe is just one bubble in a much larger, and perhaps infinite, multiversal ocean. If the model of eternal inflation is correct, then beyond the boundaries of our universe lie other universes, perhaps with different physical laws and constants. These universes would be forever beyond our reach, separated from us by an eternally expanding space. Yet, the study of the traces that inflation has left in our own universe, in the cosmic microwave background, could provide us with indirect evidence for the existence of this broader multiversal picture, a picture that would completely revolutionize our understanding of our place in the cosmos. In our exploration of what might lie beyond the boundaries of our universe, we inevitably run up against the limits of our current understanding of physics. We have two incredibly successful yet mutually incompatible theories that describe the world around us. On the one hand, we have Einstein's general theory of relativity, which masterfully explains the force of gravity as the curvature of space-time and governs the world of the very large planets, stars, and galaxies. On the other hand, we have quantum mechanics, the strange and counterintuitive theory that describes the world of subatomic particles and their interactions with stunning precision. The problem arises when we try to apply these two theories to situations where both gravity and quantum effects are important, such as in the center of a black hole or in the first moments of the Big Bang. In these extreme environments, where immense mass and energy are concentrated into an incredibly small space, our two great pillars of physics fail. General relativity predicts infinities, or singularities, which are physically nonsensical, and quantum mechanics, in its standard form, is unable to incorporate the curvature of space-time and the force of gravity into its calculations. This profound conflict has led to one of the greatest and most challenging quests in all of modern science, the search for a so-called theory of everything, a single, unified theoretical framework that would encompass all the known forces of nature, including gravity, into a single, consistent set of equations. One of the most promising and intensely studied candidates for such a theory is string theory. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, one-dimensional vibrating objects called strings. The different vibrational modes of these strings would then correspond to the different elementary particles we observe, much like the different vibrations of a violin string produce different musical notes. One of the most surprising and radical predictions of string theory is the existence of extra spatial dimensions beyond the three we commonly perceive. These extra dimensions would be curled up or compactified on such a small scale that they would be unobservable in our everyday lives. Another leading approach to the problem of quantum gravity is loop quantum gravity. This theory attempts to quantize spacetime itself. It assumes that spacetime is not a smooth but continuous fabric, but is composed of discrete, indivisible units, or quanta, at the incredibly small Planck scale, which is about 10 to the minus 35 meters. In this view, space and time have a granular or atomic structure. These theories have profound and mind-bending implications for our understanding of what might lie beyond the boundaries of our universe. If string theory is correct, our entire universe could be a kind of three-dimensional membrane, or brane, floating in the higher dimensional space known as the bulk. Other bruns representing other universes could exist parallel to our own, perhaps only a fraction of a millimeter away from us, but in another dimension that we cannot perceive. Alternatively, if loop quantum gravity is correct, spacetime would have a granular structure on the smallest scales, which could prevent the formation of singularities and could lead to scenarios like the Big Bounce, where our universe emerged from the collapse of a previous one. Despite decades of intense research by some of the brightest minds in physics, neither of these theories has yet gained any direct experimental confirmation. This reflects the extreme difficulty of testing physics at the Planck scale, which is many orders of magnitude beyond the reach of our most powerful particle accelerators. One of the strangest and most fascinating objects in the universe are black holes. These cosmic anomalies arise when a sufficiently massive star exhausts its nuclear fuel and collapses under its own immense gravity. The gravitational force becomes so strong that it creates a region of space-time from which nothing, not even light, can escape. The boundary of this region is called the event horizon. What lies beyond this event horizon? According to general relativity, all matter that crosses the horizon continues to fall inward towards a so-called singularity, a point of infinite density and curvature where all the known laws of physics break down. Here, our current physical theories fail, and we need a theory of quantum gravity to understand what is really happening at the heart of a black hole. Some speculative theories suggest that black holes could be more than just cosmic prisons. They could be portals to other universes. Such a hypothetical connection, called an Einstein-Rosen bridge or, more popularly, a wormhole, could theoretically connect two distant regions of our universe or even two different universes altogether. A classical wormhole, however, would be extremely unstable and would collapse immediately. But there are theoretical ways it could be kept open, for example, by using a hypothetical form of exotic matter with negative energy. The British physicist Stephen Hawking made a groundbreaking discovery when he showed that black holes are not completely black. Due to quantum effects near the event horizon, black holes should emit a faint thermal radiation, which is now known as Hawking radiation. Over immense timescales, this radiation would cause a black hole to lose all its mass and evaporate. This process of Hawking radiation leads to an interesting and deep puzzle known as the black hole information paradox. Quantum mechanics states that information can never be destroyed, but when an object falls into a black hole, the information about it seems to be lost forever. When the black hole later evaporates via Hawking radiation, this radiation appears to be completely random and thermal, carrying no information about what fell into the black hole. So, where does the information go? One possible solution is that the information is actually encoded on the two-dimensional surface of the black hole's event horizon. Much like a hologram, this idea led to the so-called holographic principle, which proposes that all the information contained within a volume of spacetime can be represented on the boundary of that volume. Some theoretical models even suggest that a completely new universe could be created beyond the event horizon of a black hole, expanding into its own set of dimensions. Each black hole in our universe could thus be a seed, a kind of cosmic umbilical cord to a new universe, and our own universe could have been similarly born from a black hole in some larger parent universe. These ideas remain highly speculative and are at the very frontier of what we can test with current scientific methods. Yet, mathematical models suggest that such a connection between black holes and other universes is at least theoretically possible. When we consider what lies beyond the boundaries of our universe, we cannot overlook the question of what lies before us in time. What is the ultimate fate that awaits our universe in the far distant future? Physicists and cosmologists have developed several possible scenarios for how the universe might end, each based on different assumptions about the nature of dark energy and the overall geometry of the cosmos. The first possibility is the so-called Big Crunch. If the repulsive force of dark energy were to weaken over time, or even reverse its character and become attractive, or if the total density of the universe were high enough, then gravity would eventually halt the expansion of the universe and reverse it. The universe would begin to contract, galaxies would rush towards each other ever faster, the temperature and density would rise until everything ended in a huge cosmic implosion, a fiery singularity that would be a mirror image of the Big Bang. The second, and currently most favoured, possibility is the Big Freeze, or the heat death of the universe. If dark energy is a cosmological constant, as current observations suggest, then the universe will continue to expand at an accelerating rate forever. Galaxies outside our local group will recede until they disappear from our view. Over trillions of years, star formation will cease as the interstellar gas is used up. The existing stars will one by one burn out and die, leaving behind a dark, colder universe populated only by the dead remnants of stars, like black dwarfs and neutron stars and black holes. Even these objects would eventually decay or evaporate over unimaginable timescales, leaving behind only a sparse, diffuse gas of elementary particles, all at a temperature infinitesimally close to absolute zero. The third possibility is the Big Rip. If the repulsive force of dark energy were to grow stronger over time, a more violent end could await us. The accelerating expansion of the universe would become so powerful that it would eventually tear apart all gravitationally bound structures. First, it would pull apart clusters of galaxies, then the galaxies themselves. In the final moments, it would overcome the forces holding stars and planets together. And finally, even our atoms and their nuclei would be ripped apart into a sea of unbound elementary particles. A fourth scenario is the Big Bounce. Some theories of quantum gravity suggest that when the universe contracts, as in a Big Crunch scenario, it might not collapse into a singularity. Instead, repulsive quantum effects could halt the collapse at a point of maximum density and cause it to bounce back into a new phase of expansion. In this view, our universe could be part of an eternal cycle of expansion and contraction, with each Big Bang being followed by a Big Crunch that leads to another Big Bang. Another, more exotic possibility is a false vacuum decay. Quantum field theory suggests that the current vacuum state of our universe might not be completely stable, but only metastable, like a ball resting in a small dip on the side of a large hill. A random quantum fluctuation could trigger a phase transition, causing the vacuum to tunnel to a lower, more stable energy state. This would create a bubble of true vacuum that would expand at the speed of light, changing the fundamental constants of physics and destroying everything in its path. Which of these scenarios, if any, will ultimately come to pass depends on the true nature of dark energy and the fundamental laws of physics, which are still not fully understood. Our current data favours the Big Freeze scenario, but our measurements are not yet precise enough to completely rule out the other possibilities. And, of course, there is always the possibility that new physics or unforeseen phenomena could change the fate of the universe in a way we cannot yet imagine.
What if the most profound truth of our universe is hidden not in the blazing hearts of stars or the majestic sweep of galaxies, but in the absolute and utter blackness between them? We are taught to think of space as a void, a sterile and silent stage upon which the drama of matter and energy unfolds. We imagine a place of perfect emptiness, a state of pure nothingness where no light, no sound, no particle can be found. But this intuition, as ancient and as natural as our own breath, is perhaps the most magnificent misunderstanding in the history of thought, for at the very foundation of reality, where our senses fail and our classical laws dissolve into a fog of probability, physics tells us a different story. It tells us that what we call empty space is not empty, it is not nothing. It is, instead, a seething, boiling, unimaginably energetic ocean of potential and invisible, omnipresent reality that is the source, the substance, and perhaps the destiny of everything we can see and touch. This quantum vacuum is a place where fleeting ghosts of matter, known as virtual particles, constantly erupt into existence, borrowing energy from the very fabric of spacetime for a fleeting moment before vanishing back into the abyss from which they came. This is not a theoretical fantasy. It is the engine of the cosmos. The silent, invisible hum of this quantum sea is the heartbeat of the universe, a ceaseless vibration that whispers a single, fundamental truth: absolute stillness is impossible. There is no such thing as zero. From this one radical idea, everything else follows. The universe we inhabit, with its intricate structures and immutable laws, may be nothing more than a temporary, magnificent ripple on the surface of this infinite ocean of nothing that is, in fact, everything. The stage for this cosmic drama is set by a principle that governs not just the subatomic realm, but the very nature of knowledge itself. Werner Heisenberg's uncertainty principle. In its most common form, it declares a fundamental limit to our precision. We cannot simultaneously know the exact position and the exact momentum of a particle. The more precisely we measure one, the more uncertain the other becomes, but a lesser known, yet equally profound. Formulation of this principle involves a trade-off between energy and time. It states that for very short intervals of time, the law of conservation of energy, that sacred, unbreakable rule of classical physics, can be temporarily bent. The universe, it seems, allows for a form of cosmic accounting where energy can be borrowed from the vacuum, as long as it is paid back almost instantly. The shorter the loan period, the larger the amount of energy that can be borrowed. It is within these fleeting moments of borrowed time and energy that the vacuum reveals its true, creative nature. A pulse of this borrowed energy can spontaneously manifest as a pair of particles, typically a particle, and its corresponding antiparticle, such as an electron and a positron. These are not the solid, enduring particles that constitute the world around us. They are virtual particles, ephemeral phantoms that exist on the very edge of reality. They flicker into being, interact with their surroundings, and then, within a time frame dictated by the uncertainty principle, they collide with each other and annihilate, paying back their energy debt to the vacuum and disappearing without a trace. This is not a rare or isolated event. It is happening constantly, everywhere, in every cubic centimeter of space, from the core of our sun to the most desolate void between galaxies. The quantum vacuum is a roiling foam of these appearing and disappearing virtual particle pairs. It is a world of perpetual creation and destruction, a relentless dance of existence and non-existence. To our macroscopic senses, this activity is completely invisible. The vacuum appears calm, silent, and empty, but at the quantum level, it is a chaotic and vibrant theater. Imagine a perfectly still lake. From a distance, its surface appears glassy and inert, but if you were to magnify it 1 billion times, you would see a frenzied world of water molecules in constant violent motion, colliding, vibrating, and interacting. The quantum vacuum is like this, but instead of water molecules, it is a maelstrom of every possible type of particle, each emerging from its own underlying quantum field. There is an electron-positron field, a quark-antiquark field, a photon field, and so on for every fundamental constituent of nature. These fields permeate all of space, and the virtual particles are the momentary energetic ripples upon their surfaces. This is not just a poetic metaphor. This invisible activity has real, measurable consequences. It is the very source of what we call zero-point energy, the baseline, irreducible energy that remains in a system even at a temperature of absolute zero, where all classical motion should cease. The uncertainty principle forbids a state of perfect rest. A particle cannot have zero energy, because that would imply a precise momentum zero and a precise energy zero, a violation of the fundamental rules. Therefore, even in its lowest possible energy state, a quantum system must retain a residual vibration, a quantum jitter. This zero-point energy is the energy of the vacuum itself, the energy of emptiness. The first concrete, experimental proof of this astonishing idea came in 1948 from the Dutch physicist Hendrik Casimir. He proposed a thought experiment that was later confirmed in laboratories with stunning precision. Imagine taking two perfectly smooth, uncharged metal plates and placing them parallel to each other in a perfect vacuum, separated by a distance smaller than the width of a human hair. Classically, since there is nothing between or around the plates, no force should act upon them. But Casimir realized that the quantum vacuum would behave differently in the space between the plates than in the space outside them. Outside the plates. Virtual particles of all possible wavelengths and energies can flicker into and out of existence. However, the tiny gap between the plates acts as a resonant cavity. It restricts the dance of virtual particles, allowing only those with wavelengths that fit neatly into the gap to exist. This means there are fewer possible virtual particles popping into existence inside the gap than outside it. This imbalance in the quantum foam creates a pressure differential. The greater pressure from the virtual particles in the wider vacuum outside pushes the plates together. This force, known as the Casimir effect, is incredibly small, but it is real, measurable, and undeniable. It is a force created from nothing but the geometry of emptiness itself. It is physical proof that the vacuum is not a void, but a dynamic, energetic medium that can exert a physical force on the world we see. This experiment transformed the quantum vacuum from a mathematical curiosity into a tangible, physical reality. It proved that space is not a passive backdrop, but an active participant in the workings of the universe. The silent whispers of virtual particles it turns in can move mountains, or at least microscopic metal plates. This invisible dynamism has implications that extend far beyond the laboratory. The existence of virtual particles reshapes our understanding of the fundamental forces of nature. In the framework of quantum field theory, forces are not transmitted through some mysterious, instantaneous action at a distance. Instead, they are mediated by the exchange of virtual particles. When two electrons repel each other, it is because they are exchanging virtual photons. A virtual photon is created by one electron, travels across the space between them, and is absorbed by the other, transferring momentum and energy, which manifests as the electromagnetic force. Similarly, the strong nuclear force that binds quarks together inside protons and neutrons is mediated by the exchange of virtual particles called gluons. The weak nuclear force, responsible for certain types of radioactive decay, is carried by virtual W and Z bosons. Without this constant, invisible traffic of virtual particles, the universe as we know it would fall apart. Atoms would not hold together. Stars would not shine. The forces that govern all of reality are, at their most fundamental level, a consequence of the restless energy of the void. The creative power of the vacuum is most dramatically illustrated at the edge of one of the most extreme objects in the cosmos, a black hole. Stephen Hawking theorized that the same process of virtual particle pair creation that happens everywhere in space must also happen at the event horizon, the point of no return surrounding a black hole. Ordinarily, these pairs would annihilate each other almost instantly. But at the edge of a black hole, it is possible for one particle of the pair to fall across the event horizon, while its partner escapes into space. The particle that falls in carries negative energy relative to the universe outside, which effectively reduces the mass of the black hole. The particle that escapes, now unable to annihilate with its partner, becomes a real particle, carrying positive energy away. This steady stream of real particles radiating away from a black hole is known as Hawking radiation. Over immense timescales, this process causes the black hole to lose mass and, eventually, to evaporate completely. In this extraordinary process, we see the vacuum's energy being transformed into real, tangible matter and radiation. The black hole acts as a catalyst, a cosmic midwife that helps the virtual become real. This phenomenon demonstrates that the boundary between the fleeting existence of virtual particles and the permanent reality of the particles that make up our world is not absolute. Under the right extreme conditions, the ghosts of the vacuum can be solidified into substance. The void, it seems, is not just a stage for reality, it is the wellspring from which reality can emerge. From the subtle pressure between two plates to the slow death of a black hole, the evidence is overwhelming. Space is not empty, it is a plenum, a vibrant and potent field of possibility that underpins all of existence. The greatest secret of the universe may not be what is in it, but what it is made of an infinitely creative, powerful, and ever-present nothing. The constant, restless hum of the quantum vacuum is not just a feature of our present-day universe, it is a fossil, an echo that connects us directly to the moment of creation itself. To understand this, we must journey back in time to the first fractions of a second after the Big Bang. In that primordial era, the universe was an unimaginably hot, dense, and uniform soup of energy and fundamental particles. But even in this state of near-perfect homogeneity, the laws of quantum mechanics were at play. The uncertainty principle demanded that the energy density of the nascent universe could not be perfectly uniform. There had to be tiny, microscopic fluctuations regions where the energy was infinitesimally higher or lower than the average. These were the first quantum jitters of the cosmos, the initial, random ripples in the otherwise smooth fabric of spacetime. In a slowly expanding universe, these tiny fluctuations would have remained microscopic, their effects washed out over time. But the universe did not expand slowly. According to the theory of cosmic inflation, in the first sliver of a second of its existence, from roughly 10 to the negative 36 seconds to 10 to the negative 32nd seconds, the universe underwent a period of exponential, hyper-accelerated expansion. It grew from a size smaller than a proton to larger than a grapefruit in a timescale so short it defies human comprehension. This period of inflation acted as a cosmic microscope of immense power. It took those minuscule subatomic quantum fluctuations and stretched them to astronomical proportions. Regions that were once quantumly uncertain, smaller than any atom, were inflated to become larger than entire galaxies. The tiny random energy variations in the vacuum were frozen into the expanding fabric of space-time, becoming macroscopic differences in density. Areas with slightly more energy became the seeds of higher matter density, while areas with slightly less became the seeds of cosmic voids. These primordial density fluctuations were the cosmic blueprints, the architectural plans for the entire future structure of the universe. They were the gravitational seeds around which matter would later clump, pulling in gas and dust over billions of years to form the first stars, the first galaxies, and eventually, the vast cosmic web of galaxy clusters and superclusters we observe today. Every galaxy, every star, every planet, and indeed every one of us, owes our existence to a single random quantum fluctuation that was magnified to a cosmic scale during the first moments of time. We are the descendants of a quantum jitter. We are not left to speculate about this incredible story. We can see its remnants with our own eyes. Approximately 380,000 years after the Big Bang, the universe had cooled enough for protons and electrons to combine and form the first neutral atoms. Before this moment, the universe was an opaque plasma, a dense fog where light photons was constantly scattered by charged particles, unable to travel freely. But once atoms formed, the universe suddenly became transparent. The light that was present at that moment was finally set free, and it has been traveling through the expanding universe ever since. Today, that ancient light reaches us from every direction in the sky, stretched by the expansion of space over 13.8 billion years. Its wavelength has shifted from that of visible light to microwaves. This faint, pervasive glow is the cosmic microwave background CMB. It is the oldest light in the universe, a snapshot of the cosmos as it was in its infancy. When we map the CMB with sensitive telescopes like the Planck satellite, we find that it is almost perfectly uniform in temperature, at about 2.7 degrees above absolute zero, but it is not perfectly uniform. There are tiny temperature variations, differences of just 1 part in 100,000. These minute hot and cold spots in the CMB are the direct imprints of those primordial density fluctuations, the fossilized evidence of the quantum jitters that were stretched by inflation. Looking at a map of the CMB is like looking at a photograph of the sound waves that echoed through the early universe, a celestial sonogram that reveals the seeds from which all cosmic structure grew. The largest structures in the universe today correspond perfectly to the largest temperature fluctuations in the CMB. The void, through its own inherent restlessness, wrote the script for its own evolution. The silence of space, it turns out, was never silent. It began with a whisper, a quantum fluctuation, and that whisper has since grown into the grand cosmic symphony of existence. This connection between the quantum and the cosmic forces us to reconsider the very nature of physical law. The universe appears to be governed by a principle of scale invariance, where the same fundamental processes operate at vastly different levels of reality. The same quantum uncertainty that prevents an electron from being perfectly still is also the ultimate source of the largest structures in the cosmos. This suggests a deep unity in nature, a set of rules that are not just local but universal. The quantum fluctuations are not an anomaly or a strange quirk of the subatomic world. They are the fundamental engine of cosmic structure. Without this constant, creative bubbling of the vacuum, the universe might have remained a perfectly smooth, homogeneous, and ultimately sterile place. There would have been no density variations, no gravitational seeds, no galaxies, no stars, and no life. The very possibility of complexity, of structure, of existence as we know it, is born from the inherent imperfection and restlessness of the void. Furthermore, this understanding of our origins carries profound philosophical weight. If the distribution of galaxies in the universe is the result of a fundamentally random quantum process, what does this imply about our place in the cosmos? It suggests that the existence of our galaxy, our sun, and our planet was not preordained by some deterministic plan. We are the products of a cosmic lottery, a fortunate outcome of a probabilistic roll of the quantum dice. This does not diminish our significance. Rather, it highlights the extraordinary nature of our existence. In a universe born from chaos and randomness, the emergence of order, complexity, and consciousness is a testament to the creative power of natural law. It also suggests that our universe might not be unique. The theory of eternal inflation, an extension of the standard inflation model, posits that our Big Bang was not a one-time event. Instead, the quantum vacuum is constantly spawning new universes, each born from its own inflationary fluctuation. In this grander multiverse, our cosmos is but one bubble in an infinite, effervescent sea of other bubble universes, each potentially with its own physical laws and constants. This idea, known as the multiverse, is a direct logical consequence of taking the physics of quantum fluctuations and inflation seriously. If the process happened once to create our universe, there is no reason to believe it is not happening eternally, creating an endless tapestry of worlds beyond our own. The zero-point energy of the vacuum, the driver of these fluctuations, is therefore not just a curious footnote in physics. It is the lifeblood of cosmology. It is both the source of our universe's structure and potentially the seed of infinite others. It represents a fundamental level of reality where the distinction between cause and effect becomes blurred. The fluctuations are uncaused, spontaneous events, yet they are the cause of everything that follows. This challenges our deeply ingrained classical intuition that every event must have a preceding cause. At the quantum origin of the universe, this chain of causality may simply begin, not with a first cause, but with a first chance. The echo of this beginning, preserved for all time in the gentle glow of the cosmic microwave background, is a constant reminder of our quantum origins. It is a message from the void, telling us that the universe is not a static, finished object, but an ongoing process of becoming, a story whose first chapter was written by the ceaseless, creative, and essential vibrations of emptiness itself. The vast, dark canvas of the night sky is not a symbol of absence, but a testament to the power of the invisible. It is a monument to the fact that from the smallest possible tremor, the greatest possible structures can arise. The idea that our entire universe, with its billions of galaxies and untold complexity, could have emerged from the energy of the void leads to one of the most profound and unsettling questions in all of science and philosophy: did the universe come from nothing? For millennia, this question was the exclusive domain of theologians and metaphysicians, framed by the axiom ex nihilo nihil, fit from nothing. Nothing comes. The very notion of creation from absolute nothingness seemed like a logical impossibility, a violation of the most fundamental principles of causality. Classical physics inherited this view. The laws of conservation of energy and mass dictated that something could not be created from nothing. It could only be transformed from one state to another. The universe, therefore, must have either existed eternally or been brought into being by an external, pre-existing cause. But quantum mechanics, and specifically the physics of the quantum vacuum, offers a radical third option. It redefines the very meaning of the word nothing. The nothing of modern physics is not the absolute non-existence of the philosophers. It is the quantum vacuum, a state devoid of matter and radiation. Yes, but a state teeming with potential, humming with zero-point energy, and alive with the ceaseless dance of virtual particles. This is not absolute nothingness. It is a ground state of reality, a canvas of potential that possesses physical properties and can be influenced by physical laws. So, When a physicist like Lawrence Krauss titles a book A Universe from Nothing, he is referring to this quantum vacuum. The argument, supported by theories like cosmic inflation, is that our universe could have arisen as a spontaneous quantum fluctuation within this pre-existing vacuum. Imagine the vacuum as a vast, placid ocean representing a state of zero total energy. A quantum fluctuation is like a wave that momentarily rises from the surface. This wave of energy can, under the right conditions, tunnel through a quantum barrier and inflate into a new, self-contained universe. The key to this process is the idea that the total energy of the universe might actually be zero. This may sound counterintuitive, given the immense energy locked away in all the matter and radiation we see. But matter and radiation represent positive energy. Gravity, on the other hand, can be thought of as negative energy. The gravitational potential energy of a universe full of massive objects is a negative quantity. It is theoretically possible that the positive energy of all the matter and the negative energy of all the gravity in the universe perfectly cancel each other out, resulting in a universe with a net energy of zero. If the universe's total energy is zero, then its creation from a vacuum state of zero energy does not violate the law of conservation of energy. It is, in a sense, the ultimate free lunch. The universe could have simply popped into existence without any energy cost. This concept of quantum tunneling provides a mechanism for this genesis. In the quantum world, particles can do things that are classically forbidden. A particle trapped in a valley, for instance, does not need to have enough energy to climb over the surrounding hills to escape. There is a finite, calculable probability that it can simply tunnel through the hill and appear on the other side. The universe itself might have done something similar. The state of no universe, the vacuum, can be seen as a stable valley. The state of a universe like ours is another valley. A quantum fluctuation could have caused the cosmos to tunnel from the state of non-existence into the state of existence. This event, which we call the Big Bang, would not be an explosion in a pre-existing space, but the very creation of space and time itself. This is the core of the no-boundary proposal put forward by Stephen Hawking and James Hartle. They suggested that if we trace time back towards the beginning, the distinction between time and space dissolves. Near the origin, time behaves like another dimension of space. This means the universe does not have a sharp beginning in time, no singular point where we can ask what came before. The question becomes meaningless, like asking what is north of the North Pole. The universe, in this view, is a self-contained entity that came into existence through the laws of quantum mechanics, without the need for a boundary, a beginning, or an external creator. This idea fundamentally alters the nature of the creation question. It replaces a metaphysical problem with a physical one. It suggests that the existence of our universe is not a miracle that defies explanation, but a natural, if perhaps rare, consequence of the laws of physics operating on the state of the quantum vacuum. The universe, in this framework, created itself. However, this does not fully resolve the philosophical conundrum. It pushes the question back one level. We may be able to explain the origin of our universe from the quantum vacuum, but where did the quantum vacuum and the laws of quantum mechanics come from? We have replaced the question of why is there something rather than nothing, with why are there quantum fields and physical laws rather than nothing. This is a deeper and perhaps unanswerable question. Some physicists and philosophers argue that the laws of physics might be the only logically consistent set of rules that could exist, and that the quantum vacuum is the most fundamental possible state of reality. Others suggest that we may be reaching the absolute limit of scientific inquiry, a point where questions of ultimate origins become questions of philosophy rather than empirical science. Even if we accept the universe from a quantum fluctuation model, it has staggering implications. It implies that the raw material for creating universes, the quantum vacuum, is everywhere. If a quantum fluctuation could spawn our universe, it could spawn others. This leads back to the concept of the multiverse, where our cosmos is just one of an infinite number of universes, each bubbling up from the quantum foam, each potentially with different physical constants and properties. Our universe has the specific properties that allow for the formation of stars, galaxies, and life, not because of some grand design, but because we could only have evolved in a universe that had such properties. This is the anthropic principle. Our observations of the universe are biased by the fact of our own existence. In an infinite multiverse, the existence of a universe perfectly tuned for life is not a surprise. It is a statistical inevitability. We simply live in one of the bubbles where the conditions were right. This perspective transforms our universe from a unique, singular creation into one data point in an unimaginably vast cosmic landscape. The creative power of the void, in this view, is not just the source of our universe, but the source of all possible universes. The nothingness from which we came is the ultimate fountain of everything, a generator of realities that operates on an eternal and infinite scale. The question then is not just how something came from nothing, but how everything came from it. The transition from the ethereal energy of the void to the solid, tangible world we experience is one of the most mysterious and profound processes in all of physics. While the quantum vacuum is a sea of virtual particles, these entities are, by definition, fleeting and unobservable. How, then, does this transient, ghostly reality give rise to the permanent, stable particles, the electrons, quarks, and photons that constitute matter and light? The answer lies in the concept of vacuum instability. Under normal conditions, the quantum vacuum is in its lowest energy state, a stable equilibrium. Virtual particle pairs are created and are swiftly annihilated, maintaining the overall balance. However, if a significant amount of energy is injected into a region of the vacuum, or if the vacuum is subjected to an extremely strong field, its stability can be shattered. This disturbance can provide the necessary energy to promote a virtual particle pair to a real state, preventing them from annihilating each other. The borrowed energy from the uncertainty principle is essentially repaid by the external energy source, allowing the particles to become permanent residents of our universe. This process is not just theoretical, it can be observed in a number of extreme physical environments. One of the most powerful catalysts for this transformation is a strong electromagnetic field. A theory known as the Schwinger effect predicts that if an electric field is strong enough, it can literally tear virtual electron-positron pairs out of the vacuum. The field would pull the virtual electron in one direction and the virtual positron in the opposite direction so forcefully and so quickly that they are separated before they have a chance to annihilate. Given enough energy from the field, they become a real electron and a real positron. This is the direct creation of matter from the energy of a field acting on the vacuum. While creating an electric field strong enough to observe this effect is beyond our current technological capabilities, physicists at high-power laser facilities are getting closer to achieving the necessary conditions. They aim to focus immense laser energy into a tiny volume of space, creating an electromagnetic field so intense that it makes the vacuum itself boil with real particles. This would be a direct demonstration of Einstein's famous equation, E = mc², where the pure energy of light is converted into the mass of matter, with the vacuum acting as the mediating substance. An even more dramatic example of this process occurs in the universe's most powerful particle accelerators, the regions around active black holes and neutron stars. The immense gravitational and magnetic fields in these environments can act as cosmic particle factories. As matter is pulled towards a black hole, it forms an accretion disk, a swirling vortex of superheated gas and plasma. The intense energy and fields within this disk can destabilize the vacuum, creating jets of real particles that are blasted out into space at nearly the speed of light. In this case, the gravitational energy of the infalling matter is converted, via the vacuum, into new particles. This is one of the ways in which the universe populates itself with matter, recycling energy into new forms of existence. The process of Hawking radiation at a black hole's event horizon is a more subtle, but equally profound. Example. There, the black hole's own gravitational field provides the energy to split a virtual particle pair, with one particle falling in and the other escaping as real radiation. The black hole slowly evaporates, its mass energy converted back into the particles of the Standard Model, mediated by the quantum vacuum. The most spectacular instance of this particle creation occurred during the Big Bang itself. In the first moments of the universe, the energy density was so high that the vacuum was in a state of constant, violent instability. The primordial energy of the universe was continuously being converted into torrents of real matter and antimatter particles. For every billion antimatter particles created, roughly 1,000,000,001 matter particles were created, a slight asymmetry whose origin is still one of the great unsolved mysteries of physics. As the universe expanded and cooled, the matter and antimatter particles annihilated each other, releasing a tremendous burst of energy in the form of photons, which now form the cosmic microwave background. The tiny fraction of matter that was left over, that 1 in a billion surplus, is what constitutes all the stars, galaxies, and planets we see today. All the substance of our universe is the remnant of a slight imbalance in the process of particle creation from the primordial, high-energy vacuum. This means that the very existence of a material world is a consequence of the vacuum's ability to transform energy into mass. This principle of particle creation from the vacuum has deep implications for our understanding of reality. It shows that matter is not a fundamental, immutable substance. Rather, matter is a condensed or excited state of the vacuum. It is a form that energy can take under specific conditions. An electron is not a tiny solid ball, but a localized, stable vibration in the universal electron field. The vacuum is the ground state of this field, its lowest energy configuration. An electron is an excited state, a ripple on that field that we perceive as a particle. This perspective, which is the foundation of quantum field theory, tells us that the universe is not made of particles. The universe is fields. The particles are just the temporary or stable manifestations of the energy within these fields. Therefore, the vacuum is not just the source of particles, it is the underlying substance of which they are made. The journey from the energy of nothingness to the reality of matter is not a journey from one place to another, but a change of state. It is like the transition of water from invisible vapor to a visible cloud. The substance remains the same, only its form has changed. In the same way, the energy of the vacuum can condense into the matter of our world, revealing that the divide between emptiness and substance is not a sharp line, but a permeable, dynamic boundary that the universe crosses every moment, in every corner of its existence. The realization that the universe is fundamentally composed of invisible, omnipresent quantum fields forces us to confront a profound epistemological challenge. How can we consider something to be real if we cannot see it, touch it, or directly measure it? Our minds are conditioned by evolution to trust our senses. We accept the reality of a stone because we can hold it, the reality of light because we can see it. But quantum fields exist in a realm beyond direct perception. They are not material objects in the classical sense. They are abstract, mathematical constructs that describe the potential for reality at every point in space and time. This invisible nature seems to contradict our intuitive definition of what it means to be real. Yet, modern science has repeatedly taught us that the limits of our perception are not the limits of reality. The wind is invisible, but we know it is real because we can feel its force and see its effect on the swaying trees. The force of gravity is invisible, but its reality is undeniable every time we drop an object. In the same way, we know quantum fields are real not by observing the fields themselves, but by meticulously measuring their effects. Every particle that has ever been detected in a particle accelerator, from the electron to the Higgs boson, is considered to be an excitation, a localized vibration, of its corresponding underlying field. The discovery of the Higgs boson at the Large Hadron Collider in 2012 was not just the discovery of a new particle, it was the confirmation that the Higgs field, a quantum field that permeates all of space and is responsible for giving fundamental particles their mass, is a real and physical entity. The Higgs boson was merely the ripple we managed to create on its surface, the evidence of the invisible ocean beneath. The influence of these invisible fields is not confined to the exotic world of high-energy physics. It is woven into the fabric of our everyday lives and the technologies we depend on. The screen on which you are likely reading this text operates based on the principles of quantum mechanics, which are themselves a description of the behavior of electrons within the electron field. The laser in a Blu-ray player or a barcode scanner works by manipulating the coherent states of photons within the electromagnetic field. The semiconductors and transistors that form the heart of every computer and smartphone are devices engineered to control the flow of electrons through carefully structured materials, a process governed entirely by the rules of quantum field theory. Medical technologies like magnetic resonance imaging (MRI) rely on manipulating the quantum property of spin in the nuclei of atoms, another manifestation of the underlying quantum fields. The global positioning system GPS in your phone would be inaccurate by several kilometers a day if it did not account for the effects of both special and general relativity. Theories that describe how time and space, the very stage for these fields, are themselves dynamic. In each of these cases, we are harnessing the predictable and measurable effects of an invisible reality. If the quantum fields were not real, none of these technologies would work. Their consistent and reliable operation is a daily, practical proof of the existence of this unseen layer of reality. The philosophical implications of this are immense. It forces us to adopt a more sophisticated and less naive view of what constitutes reality. Science does not define real as that which can be seen. It defines real as that which has a measurable and predictable effect on the physical world. By this standard, quantum fields are not just real, they are the most fundamental layer of reality that we have so far discovered. They are the software of the universe, the underlying code that dictates the behavior of all matter and energy. The particles we observe are like the pixels on a screen, the visible output of a much deeper and more complex program running in the background. To believe that only the visible world is real is like believing that a computer game is nothing more than the images on the monitor, without acknowledging the existence of the software, the processor, and the electricity that make it possible. It is a form of sensory chauvinism, a prejudice that reality must conform to the limited toolkit of human perception. This shift in understanding represents a kind of metaphysical enlightenment. It is the realization that the world we see is an emergent phenomenon, a surface manifestation of a deeper, invisible order. This has parallels in the history of human thought. For centuries, people believed that life was imbued with a mystical, vital force that distinguished it from non-living matter. The discovery of biochemistry and molecular biology revealed that life is an emergent property of complex chemical interactions, governed by the same physical laws that apply to inanimate objects. The mystery was not removed, it was deepened and made more profound. Similarly, the discovery of quantum fields does not remove the mystery of existence, it reframes it. The question is no longer just what is the world made of, but what is the nature of the invisible fields from which the world is made. The fact that we cannot see these fields with our naked eyes does not make them imaginary. On the contrary, it may be our belief that reality is limited to what we can see that is the true fantasy. The invisible quantum fields are not just a part of the universe, they are the universe. Everything else is just commentary. The question of why there is something rather than nothing is perhaps the most ultimate question a conscious mind can ask. It stands at the precipice of physics, philosophy, and theology, challenging the very foundations of our understanding of existence. For most of human history, the answer has been framed in terms of causality and necessity. Something must exist because something has always existed, or because something was created by a necessary, external being. The assumption has always been that nothingness is the default state, a simple, stable, and natural condition, and that the existence of something as complex and ordered as our universe is the anomaly that requires a special explanation. Quantum physics, however, invites us to turn this ancient assumption on its head. It suggests that perhaps absolute nothingness is the one state that is physically impossible. Perhaps it is existence, in some form, that is the natural, inevitable, and default state of reality. The argument begins, once again, with the quantum vacuum. As we have seen, the vacuum is not a state of absolute nothingness. It is a state of minimum energy, but that energy is not zero. It is alive with zero-point fluctuations. The laws of quantum mechanics, as we currently understand them, seem to forbid a state of perfect, absolute non-existence. The uncertainty principle dictates that there must always be some residual energy, some inherent restlessness, in the fabric of reality. If the laws of physics themselves require that something must always be fluctuating, even in a vacuum, then the state of absolute nothing, a state with no energy, no fields, no fluctuations, and no physical laws may be a logical contradiction, an idea that cannot be realized in the physical world. This leads to a provocative and powerful idea. Maybe the reason there is something rather than nothing is because nothing is unstable. Imagine a perfectly sharpened pencil balanced on its tip. This state of perfect symmetry is analogous to a state of absolute nothingness. While it is theoretically possible, it is exquisitely unstable. The slightest perturbation, a quantum fluctuation, will cause the pencil to fall, breaking the symmetry and creating a specific outcome. It falls in a particular direction. Similarly, a hypothetical state of perfect symmetric nothingness might be inherently unstable. A spontaneous quantum fluctuation could shatter this symmetry, causing a universe to emerge, just as the pencil falls. In this view, the Big Bang was not the creation of something from nothing, but the collapse of an unstable nothingness into a more stable state of somethingness. Existence, therefore, is not a violation of the natural order. It is the resolution of an unstable void. The universe exists for the same reason a ball rolls downhill. It is moving towards a state of greater stability. This perspective is bolstered by models that propose the total energy of the universe is zero. If the positive energy of matter and radiation is perfectly balanced by the negative energy of gravity, then the universe didn't require any net energy to come into being. The creation of a zero-energy system from a state of zero energy is not a violation of any conservation law. It is a permissible, and perhaps even a probable, quantum event. This reframes the entire problem. The question is no longer why did the universe come into being, but was there anything to prevent it? If the laws of physics allow for the spontaneous creation of a zero-energy universe from an unstable vacuum, and there is no law that forbids it, then over an infinite amount of time or outside of time altogether, such an event is not just possible, but statistically inevitable. In a multiverse context, where an infinite number of quantum fluctuations are occurring, it is virtually certain that some of them will blossom into universes like ours. We exist because it was bound to happen somewhere, sometime. This approach removes the need for a first cause or an external creator in the traditional sense. The universe is not a product of external intervention, but an emergent property of the fundamental laws of nature operating on a quantum substrate. However, this still leaves us with the deeper philosophical question, why these laws? Why the laws of quantum mechanics? Why a universe where the total energy is zero? We have not eliminated the question of ultimate origins. We have simply pushed it from the realm of cosmology to the realm of fundamental physics and mathematics. Is there a single, unique set of physical laws that is logically necessary? Or are the laws themselves contingent, just another outcome of a random process in a grander metaverse? This is where the boundary between science and metaphysics becomes truly blurred. Science can describe how the universe might have emerged from a quantum vacuum according to a set of laws. It cannot, at present, explain why that vacuum or those laws exist in the first place. Ultimately, the question why is there something rather than nothing may be a question born from the limitations of human intuition. Our minds evolved in a macroscopic, classical world of cause and effect, where things do not pop into existence unbidden. We project this intuition onto the cosmos and find its uncaused existence to be a puzzle. But the universe is not obligated to conform to our intuition. The quantum realm operates on a different logic, a logic of probability, potentiality, and spontaneous fluctuation. From the perspective of quantum physics, the existence of something might be the most natural thing in the world. Perhaps the deepest paradox is our own expectation of nothingness. We look out at the vast, intricate, and astonishing reality of the cosmos and find it surprising. But maybe, just maybe, the universe looks back at us and finds our question even stranger. It exists because, at the most fundamental level, it couldn't not exist. Existence may not be the exception, it may be the rule.
Imagine an object so dense, so heavy, that its own gravity becomes an inescapable trap. Picture a point in space where the familiar rules of our universe are bent and broken, where time itself can grind to a halt, and where not even light, the fastest thing in the cosmos, can escape. This is the world of the black hole, one of the most extreme and enigmatic phenomena in all of nature. According to Albert Einstein's general theory of relativity, when a sufficient amount of matter is compressed into a sufficiently small volume, the force of gravity becomes so overwhelming that it creates a one-way membrane in space-time, a point of no return known as the event horizon. Anything that crosses this boundary is lost to the outside universe forever, pulled inexorably towards a central singularity, a point of infinite density where our current laws of physics break down. The size of this event horizon, the Schwarzschild radius, depends on the mass of the object. For our own sun to become a black hole, it would need to be squeezed down to a diameter of just 3 kilometers. At that point, its density would be astronomical, far beyond anything we encounter in our everyday world. For smaller objects, the powerful quantum forces that operate between subatomic particles, the electromagnetic force and the nuclear forces, are strong enough to resist the inward pull of gravity, preventing them from collapsing into such an extreme state. But for the most massive stars in the universe, a different fate awaits. Black holes are not just a theoretical curiosity. They are a ubiquitous feature of our cosmos, and they come in a vast range of sizes. Stellar mass black holes are the ghosts of dead stars. When a star, more than about 10 times the mass of our Sun, exhausts its nuclear fuel, it can no longer support its own weight against the crushing force of gravity. Its core collapses catastrophically, triggering a spectacular supernova explosion that blasts its outer layers into space. What remains behind is a compact remnant, a black hole with a mass a few times that of our Sun. Our own Milky Way galaxy is thought to be littered with over 1 billion of these stellar ghosts, most of them dark and invisible, wandering silently through the interstellar void. We can only detect them indirectly when they are locked in a binary system with a normal star, their immense gravity pulling material from their companion into a glowing, superheated accretion disk. At the other end of the scale are the supermassive black holes, the true giants of the cosmos. These behemoths, with masses ranging from millions to billions of times that of our Sun, are thought to reside at the heart of nearly every large galaxy, including our own. At the center of the Milky Way lurks Sagittarius A, a supermassive black hole with a mass of about 4 million suns. These galactic monsters are the engines that power the most luminous objects in the universe, quasars. A quasar is an incredibly bright, distant galactic nucleus, where a supermassive black hole is actively feeding on a vast disk of gas and dust, releasing an amount of energy that can outshine its entire host galaxy by a factor of thousands. Between these two extremes lies a more elusive class, intermediate mass black holes. These are thought to form from the collapse of the very first generation of stars, population 3 stars, which were much more massive than the stars we see today, with masses over 100 times that of our Sun. These primordial giants would have burned through their fuel very quickly, collapsing directly into intermediate mass black holes and potentially triggering some of the powerful gamma ray bursts we observe in the distant universe. All of these black holes, from the stellar to the supermassive, are considered macroscopic. They are large enough that their behavior is, for the most part, well described by the classical laws of Einstein's general relativity. But there may be another, much stranger, class of black holes, a class for which the bizarre rules of the quantum world become all important. These are the primordial black holes, hypothetical objects that may have formed not from the collapse of stars, but from the extreme, high-density conditions of the very early universe, just a fraction of a second after the Big Bang. These primordial black holes could have a vast range of masses, from the supermassive down to the microscopic. A primordial black hole with a mass less than that of our Moon could be smaller than a micron. Yet its gravitational influence could still be significant, and some have speculated that these objects could even constitute the mysterious dark matter that makes up the bulk of the universe's mass. It is at this microscopic scale that our classical understanding of black holes begins to break down, and a new, more profound, and more mysterious picture begins to emerge. In 1974, the physicist Stephen Hawking made a discovery that would forever change our understanding of black holes and would forge a deep and unexpected link between the two great pillars of modern physics, general relativity and quantum mechanics. He showed that black holes are not, in fact, completely black. Due to quantum effects at the very edge of the event horizon, they should slowly emit a faint thermal radiation, now known as Hawking radiation. This discovery was a theoretical tour de force, a beautiful and subtle calculation that showed how the constant roiling sea of virtual particles in the quantum vacuum could be influenced by the intense gravity of a black hole. In the empty space near an event horizon, a virtual particle-antiparticle pair can be created. Normally, this pair would quickly annihilate each other and disappear. But if one particle falls into the black hole while the other escapes, the escaping particle can become a real particle, carrying away a tiny amount of the black hole's mass energy. The black hole, in effect, radiates. The temperature of this radiation is inversely proportional to the black hole's mass. The smaller the black hole, the hotter it is, and the more rapidly it radiates. For a large, stellar mass black hole, this temperature is incredibly low, far colder than the cosmic microwave background, making the radiation practically undetectable. But for a small, primordial black hole, the temperature could be incredibly high. A black hole with the mass of a large mountain would have a temperature of about 10 to the power of 12 Kelvin, and it would radiate away its mass not just as photons, but as a shower of electrons, positrons, and other energetic particles. This process of radiation means that black holes are not eternal. They evaporate. As a black hole radiates, it loses mass, which, due to the inverse relationship, causes it to get hotter and radiate even faster. This creates a runaway process, an accelerating evaporation that culminates in a final, explosive burst of energy. The lifetime of a black hole depends dramatically on its initial mass. A solar mass black hole would take an almost unimaginable 10 to the power of 64 years to evaporate, far longer than the current age of the universe. But a primordial black hole with a mass of about 10 to the power of 12 kilograms would have a lifetime of roughly 10 billion years, about the age of our universe. This means that such black holes, if they were formed in the Big Bang, should be exploding right now, releasing their final energetic death cry in a flash of gamma rays. The search for these telltale flashes is an active, if so far unsuccessful, area of observational astronomy. The black holes that are small enough to be significantly affected by these quantum processes. Those with masses below about 10 to the power of 12 kilograms are what we call quantum black holes. Their behavior is no longer governed solely by classical gravity, but by a complex interplay between general relativity, quantum field theory, and thermodynamics. Hawking's discovery was a monumental first step towards a unified theory of quantum gravity, a theory that could describe the universe at its most extreme and fundamental level. But it was only a first step. His analysis was semi-classical, meaning it treated the radiating particles quantum mechanically, but treated the space-time of the black hole classically. A full understanding of the formation and evaporation of the smallest possible black holes. Those with a mass and size approaching the Planck scale, the fundamental limit where the effects of quantum gravity become dominant, will require a true, and as yet undiscovered, theory of everything. Such a theory might reveal even stranger possibilities, such as the idea that an evaporating black hole does not disappear completely, but leaves behind a tiny, stable, Planck mass relic, a quantum fossil that could hold the secrets of the information that fell into the black hole. The quest for a theory of quantum gravity, the holy grail of modern theoretical physics, has led scientists down a number of strange and beautiful paths. And one of the most intriguing of these is the idea of extra hidden dimensions of space. This is a concept that dates back to the 1920s, when the physicists Theodore Kaluza and Oscar Klein proposed that our universe might have a fifth dimension, a dimension that is curled up or compactified into a tiny circle at every point in our familiar three-dimensional space. They showed that if this were the case, then Einstein's theory of gravity in 5 dimensions would look, in our 4-dimensional world, like a combination of gravity and electromagnetism. It was a beautiful and elegant idea, a first, tantalizing hint that the different forces of nature could be unified through the geometry of higher dimensions. The idea of extra dimensions was later revived and expanded in the context of string theory. In its modern form, known as M-theory, the theory requires the existence of a total of 11 spacetime dimensions, 10 of space and 1 of time. The extra 7 spatial dimensions are thought to be curled up into a complex, 6-dimensional geometrical shape known as a Calabi-Yau manifold. The precise shape and size of this manifold determines the vibrational patterns of the fundamental strings, and therefore, the properties of all the particles and forces in our universe. In the standard picture, these extra dimensions are thought to be incredibly small, on the order of the Planck length. This would mean that they have no noticeable effect on the behavior of macroscopic black holes. But in some, more recent, brane world models, it is possible that some of these extra dimensions are much larger. In these models, the particles and forces of the standard model are confined to our 3-dimensional brane, while gravity is free to propagate in the higher dimensional bulk. This could have a dramatic effect on the strength of gravity at short distances. The familiar inverse square law of gravity would break down, and gravity would become much, much stronger at scales comparable to the size of the extra dimensions. This has a profound implication, the true of fundamental scale of quantum gravity. The Planck scale could be much lower than the traditional value of 10 to the power of 19 giga electron volts. It could, in fact, be as low as a few tera electron volts, a range of energy that is just now being probed by our most powerful particle accelerator, the Large Hadron Collider. This raises the astonishing and exciting possibility that we could create microscopic quantum black holes in the laboratory. The LHC works by accelerating protons to nearly the speed of light and then smashing them together. Each proton carries an energy of around 7 tera electron volts. In a head-on collision, the total energy is 14 tera electron volts, all concentrated in a tiny subatomic volume. In the standard picture of gravity, this is far, far too low an energy to create a black hole. The proton's mass is about 10 to the power of 19 times smaller than the Planck mass, and the density achieved in a collision is many orders of magnitude below the Planck density required for gravitational collapse. To create a black hole in a collision, we would need to accelerate a proton to the Planck energy, an energy that is a quadrillion times higher than what the LHC can achieve. Building such an accelerator would require a machine the size of our galaxy. But if the idea of large extra dimensions is correct, and the true Planck scale is in the tera electron volt range, then the story changes completely. The high-energy collisions at the LHC could, in principle, have enough energy to briefly compress a sufficient amount of mass energy into a small enough volume to create a tiny microscopic black hole. These would not be the dangerous galaxy-eating monsters of science fiction. They would be subatomic in size, and they would evaporate almost instantaneously, in about 10 to the power of minus 27 seconds, via Hawking radiation. They would decay into a spectacular, spherical burst of high-energy particles, photons, electrons, quarks, gluons that would light up our detectors like a microscopic firework, a unique and unmistakable signature of new, exotic physics. The search for such events has been one of the major goals of the LHC experimental program. So far, no evidence for the production of microscopic black holes has been found. This has placed strong constraints on many of the models with large extra dimensions, pushing the possible scale of quantum gravity to higher and higher energies. But the search continues. The discovery of microscopic black holes at the LHC would be a scientific revolution of the highest order. It would be the first direct experimental evidence for the existence of extra dimensions of space. It would provide us with a laboratory to study the physics of quantum gravity. to test the predictions of Hawking radiation, and to probe the very fabric of space-time at its most fundamental level. It would be a window into a new, hidden reality. A reality that has, until now, been completely inaccessible to us. The discovery of Hawking radiation and the subsequent paradox of information loss has been one of the most powerful drivers of theoretical progress in physics for the past 50 years. It is a problem that lies right at the intersection of our two most fundamental theories, general relativity and quantum mechanics, and its resolution is thought to be a crucial key to unlocking the secrets of quantum gravity. At its heart, the paradox is a clash of two, seemingly inviolable principles. General relativity, with its description of a smooth space-time and an absolute event horizon, seems to imply that any information that falls into a black hole is lost to the outside universe forever, causally disconnected and irretrievable. Quantum mechanics, on the other hand, insists on the principle of unitarity, the idea that information is never truly destroyed. The total amount of information in a closed system must be conserved. A process may be scrambled, its information hidden in complex correlations, but it can, in principle, always be unscrambled. So, what happens when a black hole, which has swallowed a vast amount of information, completely evaporates into a seemingly random thermal bath of Hawking radiation? Is the information lost, in violation of quantum mechanics, or does it somehow get out, in violation of general relativity's principle of locality and causality? This is the information paradox for many years. Stephen Hawking himself was a firm believer in information loss. He argued that the process of black hole evaporation was fundamentally non-unitary, and that we would have to modify the laws of quantum mechanics to accommodate it. But most of the theoretical physics community, particularly those working in string theory, resisted this conclusion. The principle of unitarity is so central to the structure of quantum mechanics that to abandon it would be to abandon the very foundations of our most successful physical theory. This led to a decades-long search for a mechanism by which the information could escape. One of the most powerful and influential ideas to emerge from this search is the holographic principle, first proposed by Gerard Hooft and later developed by Leonard Susskind. The principle was motivated by the discovery that the entropy of a black hole, its information content, is proportional not to its volume, as one might expect, but to the area of its event horizon. This is a strange and profound result. It suggests that all the information about the three-dimensional interior of a black hole can be somehow encoded on its two-dimensional surface. This is like a hologram, where a two-dimensional film can encode all the information needed to create a three-dimensional image. The holographic principle generalizes this idea to the entire universe. It suggests that the reality we perceive as a three-dimensional space with gravity might be a holographic projection of a more fundamental two-dimensional quantum field theory that lives on the boundary of our space-time, a theory that does not include gravity. This is the essence of the ADS-CFT correspondence, a specific and powerful mathematical realization of the holographic principle discovered by Juan Maldacena, which shows an exact equivalence between a theory of gravity in a five-dimensional anti-de Sitter space and a four-dimensional quantum field theory living on its boundary. This correspondence provides a powerful tool for studying quantum gravity, as it allows us to translate difficult problems in gravity into more tractable problems in a non-gravitational quantum field theory, a theory that is, by definition, unitary. In the context of the information paradox, the holographic principle suggests that the information is never truly inside the black hole in the classical sense. It is stored on the event horizon, and as the black hole evaporates, this information is slowly and subtly encoded in the quantum correlations of the outgoing Hawking radiation. The process is unitary. and no information is lost. Another, more recent, and even more startling idea is the ER-EPR conjecture, proposed by Leonard Susskind and Juan Maldacena. This conjecture proposes a deep and unexpected connection between two of Einstein's most famous ideas: the spooky action at a distance of quantum entanglement and the concept of a wormhole or Einstein-Rosen bridge. The conjecture states that two entangled particles are, in a sense, connected by a microscopic, non-traversable wormhole. The strange, non-local correlation of entanglement is a manifestation of this deep, geometrical connection in space-time. In the context of a black hole, this idea has profound implications. The outgoing Hawking radiation is entangled with the particles that fell into the black hole. The ERR-EPR conjecture would suggest that the inside of the black hole is geometrically connected to the outgoing radiation via a vast network of microscopic wormholes. The information is not trapped inside. It is non-locally connected to the outside. These are highly abstract and mathematical ideas, and they are still the subject of intense research and debate. But they are a testament to the incredible creativity and power of theoretical physics. They show how a deep conceptual paradox, born from the clash of our two greatest theories, can become a powerful engine for discovery, leading us to new and profound insights into the nature of space-time, of information, and of reality itself. The black hole information paradox is not just a technical puzzle. It is a koan, a riddle that is forcing us to abandon our classical intuitions and to embrace a new, more holistic and more deeply quantum vision of the cosmos. The formation of black holes is a story of gravitational triumph, a cosmic drama where the relentless inward pull of gravity overcomes all other forces of nature. The most common pathway to a black hole is through the death of a massive star. A star, for most of its life, is a battlefield, a delicate balance between two opposing forces. Gravity, the force that pulls all of its matter inwards, is constantly trying to crush the star. This is counteracted by the outward pressure generated by the intense heat and radiation from the nuclear fusion reactions in its core. As long as the star has fuel to burn, this hydrostatic equilibrium is maintained. But when a massive star, one with a mass more than about 25 times that of our Sun, exhausts its nuclear fuel, the story changes. The fusion reactions in its core cease, the outward pressure vanishes, and gravity wins. The core of the star collapses catastrophically under its own immense weight. This collapse is an incredibly rapid and violent event. In a fraction of a second, a region of matter the size of the Earth is crushed down to a size smaller than a city, reaching densities that are almost beyond comprehension. The outer layers of the star, no longer supported by the core, come crashing down, bounce off the super-dense, newly formed protoneutron star, and are blasted out into space in a spectacular supernova explosion, one of the most energetic events in the universe. But for the most massive stars, even the immense pressure of the neutrons, the neutron degeneracy pressure that supports a neutron star, is not enough to halt the collapse. The gravitational pull is so overwhelming that the core continues to collapse indefinitely, down to a point of infinite density, a singularity. An event horizon forms around this singularity, and a new stellar mass black hole is born. This is the standard picture, but recent observations and theoretical work have revealed a more complex and nuanced story. For stars in a certain mass range, roughly between 8 and 25 solar masses, the collapse of the core can be temporarily halted, forming a neutron star. But the fallback of material from the supernova explosion can then push the mass of the neutron star over its critical limit, causing it to subsequently collapse into a black hole. For even larger stars, those with masses above about 40 times that of the Sun, The collapse can be so rapid and so powerful that it does not even produce a traditional supernova. The star collapses directly into a black hole, swallowing its own explosion in a phenomenon known as a collapser. These events are thought to be the engines behind some of the most powerful explosions in the universe, the long-duration gamma-ray bursts. The formation of supermassive black holes, the behemoths that reside at the centers of galaxies, is a more complex and still not fully understood story. They are too massive to have formed from the collapse of a single star. Instead, they are thought to have grown over cosmic time through a combination of processes. They may have started as seed black holes in the early universe, either from the collapse of the very first massive population 3 stars, or from the direct collapse of vast clouds of primordial gas. These seed black holes would have then grown over billions of years by accreting gas and dust from their host galaxies, and by merging with other black holes during galactic collisions. The James Webb Space Telescope is providing crucial new insights into this process by observing some of the most distant quasars, which are powered by supermassive black holes that had already grown to billions of solar masses when the universe was less than 1 billion years old. The existence of these massive black holes so early in cosmic history is a major challenge to our models of their formation and growth, suggesting that the process may have been much more rapid and efficient than we previously thought. The formation of a black hole is not just an astrophysical event, it is a transformation of the very fabric of reality. A place where matter is crushed out of existence and the laws of physics are pushed to their absolute limits. It is a one-way journey into a realm of mystery, a place from which no information can return. Or so we thought. The no-hair theorem is a profound and elegant statement about the nature of black holes in the context of classical general relativity. It is a concept that strips black holes of all their complexity and reduces them to objects of almost perfect simplicity. The theorem, which was developed through the work of physicists like Werner Israel, Brandon Carter, and Stephen Hawking, states that a stable, stationary black hole, regardless of the intricate details of the matter that collapsed to form it, can be completely and uniquely described by just 3, and only 3, externally observable properties: its total mass, its total electric charge, and its total angular momentum, or spin. All other information about the matter that fell in its chemical composition, its temperature, its shape, its texture is seemingly lost forever behind the event horizon. The black hole, in this sense, has no hair. It has no other distinguishing features, no complex individual characteristics. All black holes with the same mass, charge, and spin are identical and indistinguishable from the outside. This is a remarkable statement. It means that if you were to make a black hole by collapsing a vast cloud of hydrogen gas, and another black hole of the same mass by collapsing a collection of old television sets, the final, stable black holes would be absolutely identical. The immense complexity and information content of the initial matter is wiped clean, leaving behind only the 3 conserved quantities of mass, charge, and angular momentum. The no-hair theorem is a powerful illustration of the information loss problem. It is the classical statement that a black hole is a perfect information sink. The geometry of spacetime around a black hole is determined solely by these 3 parameters. A non-rotating, uncharged black hole is described by the simple Schwarzschild metric. A rotating black hole is described by the Kerr metric, and a charged, non-rotating black hole is described by the Reissner-Nordstrom metric. The most general case, a rotating, charged black hole, is described by the Kerr-Newman metric. These 4 solutions to Einstein's field equations are thought to describe all possible, stable, black holes in our universe. This simplicity, however, is a feature of the classical world. When we begin to consider the quantum nature of black holes, the picture becomes more complex. Quantum mechanics suggests that black holes should have a vast number of internal microscopic states, a microscopic hair that is not visible from the outside. The entropy of a black hole, which is proportional to the area of its event horizon, is a measure of this hidden internal information. The challenge for a theory of quantum gravity is to provide a microscopic, statistical explanation for this entropy. To count the number of quantum states that correspond to a given macroscopic black holes. String theory, for example, has had some remarkable successes in this area. Being able to precisely calculate the entropy of certain highly symmetric, extremal black holes by counting the number of ways that fundamental strings and branes can be configured to produce the same mass, charge, and spin. This is seen as one of the major triumphs of the theory, a sign that it is on the right track towards a quantum description of gravity. The no-hair theorem, then, may be a classical approximation. From a distance, a black hole may appear simple and featureless, but up close, at the quantum level, it may be a rich and complex object. Its event horizon a shimmering, holographic surface that encodes a vast amount of hidden information. The question of whether this information is ultimately lost or preserved is the question that lies at the heart of the information paradox, and it is a question that will likely not be fully answered until we have a complete and consistent theory of quantum gravity. The theoretical possibility of creating microscopic black holes in high-energy particle collisions, while still unconfirmed, has opened up a fascinating new frontier in experimental physics. It is an idea that connects the largest objects in the universe with the smallest, the force of gravity with the world of particle physics, and it offers a potential, albeit challenging, path to probing the exotic realm of quantum gravity in the laboratory. The production of a black hole in a collision is governed by a simple principle known as the Hoop conjecture, proposed by the physicist Kip Thorne. It states that a black hole will form if, and only if, a sufficient amount of mass energy is compressed into a region of space that is smaller than its own Schwarzschild radius. In the context of a particle collision, this means that the two colliding particles must get closer to each other than the Schwarzschild radius corresponding to their total center of mass energy. In the standard four-dimensional picture of gravity, this is an impossible feat for any conceivable particle accelerator. The Planck energy. The energy at which gravitational effects become strong is about 10 to the power of 16 times higher than the energy of the LHC. But in models with large extra dimensions, as we have seen, the true scale of quantum gravity could be much lower, potentially within the reach of the LHC. If this is the case, then in a tiny fraction of the proton-proton collisions at the LHC, the two colliding partons could get close enough to form a microscopic black hole. The probability, or cross-section, for this process can be estimated using simple, geometrical arguments. It is roughly equal to the geometric area of the black hole's event horizon, which is proportional to the square of its Schwarzschild radius. The details of the process are complex, involving the gravitational shock waves of the two ultra-relativistic particles, a phenomenon described by the Eichelberg-Sechsel metric. But the basic idea is that a closed trapped surface, the mathematical definition of an event horizon, can form in the collision, signaling the birth of a black hole. These microscopic black holes would be incredibly unstable, evaporating almost instantaneously through Hawking radiation. The specific way they decay, however, would be a powerful probe of new physics. In the standard model, a black hole should radiate democratically, emitting all types of particles with a probability that depends only on their mass and spin. But in models with extra dimensions, the black hole could preferentially radiate particles into the higher dimensional bulk, such as gravitons. This would result in a missing energy signature in our detectors, a telltale sign of the existence of extra dimensions. The Hawking radiation from these black holes would also be thermal, with a temperature that depends on the black hole's mass. by measuring the spectrum of the decay products. We could, in principle, measure the temperature of the black hole and test the predictions of Hawking's theory. Furthermore, the final stages of the black hole's evaporation, when it reaches the Planck scale, are a realm where a full theory of quantum gravity is needed. The specific particles and energies emitted in this final burst could provide crucial clues about the nature of this ultimate theory. Are they stable? Planck mass remnants is information preserved. The decay of a microscopic black hole would be a window into the most fundamental secrets of nature. The search for these exotic events at the LHC has, so far, come up empty. No signs of black hole production have been observed. This has placed stringent limits on the models with large extra dimensions, pushing the possible scale of quantum gravity to ever higher energies. It seems that if extra dimensions exist, they are smaller, or their geometry is more complex than the simplest models predicted. But the quest is not over. The LHC is continuing to collect data at higher energies and higher luminosities. And future. More powerful accelerators are being planned. The dream of creating a black hole in the laboratory, of holding a piece of quantum spacetime in our hands, is a dream that still inspires and motivates a generation of physicists. It is a long shot, to be sure, but it is a shot worth taking. For the scientific prize would be nothing less than a revolution in our understanding of the universe. In the absence of direct experimental evidence for quantum gravity from particle accelerators, physicists have turned to another, more subtle and more theoretical approach, effective field theory. This is a powerful and pragmatic framework that allows us to study the low-energy consequences of a high-energy theory without knowing all the details of that theory. The basic idea is to integrate out the high-energy physics, to average over the effects of the heavy, unknown particles and the quantum gravitational fluctuations, and to see what subtle, residual effects they leave behind on the low-energy physics that we can observe. In the context of quantum gravity, this means that we can write down and Oort effective action for our low-energy world, which consists of Einstein's general relativity and the standard model of particle physics, plus an infinite series of small, higher-dimensional correction terms. These correction terms are suppressed by powers of the Planck scale, the fundamental scale of quantum gravity. They represent the faint, low-energy echoes of the unknown. High-energy physics. While these effects are incredibly small, they are, in principle, measurable. And by precisely measuring the properties of particles and forces at low energies, we can place constraints on the possible values of the coefficients of these correction terms, giving us an indirect, but powerful, glimpse into the nature of quantum gravity. One of the most important of these correction terms is a potential non-minimal coupling between the Higgs boson and the curvature of spacetime. The Higgs boson is a unique and special particle. It is the only fundamental scalar particle in the Standard Model, and its associated field, the Higgs field, is what gives mass to all the other fundamental particles. It is natural to expect that the Higgs field would have a direct coupling to the geometry of spacetime, a coupling that is represented by a term in the effective action. This coupling has profound cosmological implications. In the early universe, during the period of cosmic inflation, the Higgs field itself could have played the role of the inflaton, the field that drove the exponential expansion. This is the idea behind Higgs inflation models. The viability of these models depends crucially on the value of this non-minimal coupling constant. By precisely measuring the properties of the cosmic microwave background, which carries the imprint of the inflationary epoch, we can place constraints on these models and, indirectly, on the nature of the interaction between the Higgs field and gravity. Another, related area of research is the effect of these quantum gravitational corrections on the unification of the fundamental forces. In grand unified theories, the strong, weak, and electromagnetic forces are all thought to emerge from a single unified force at very high energies. The success of these theories depends on the precise way that the strengths of the three forces evolve with energy and meet at a single point. The quantum gravitational correction terms can affect this running of the coupling constants, potentially altering the predictions of GUTs and offering a new way to probe the physics at the unification scale. Effective field theory is a subtle and powerful tool. It allows us to make progress in the absence of a complete theory. It is a way of listening for the faint, low-frequency whispers of the high-energy, quantum gravitational world. And while it may not give us the full symphony, it can provide us with crucial notes, with hints and clues that can guide us in our long and difficult quest to construct a final, unified theory of everything. It is a beautiful example of how precision measurements in the world we can access can shed light on the deep and mysterious realities of the world we cannot. The world of quantum gravity is not just a world of microscopic black holes and extra dimensions. It is a world where the very concepts of causality and locality, the bedrock of our classical intuition, may break down. In a classical relativistic world, information cannot travel faster than light, and events can only be influenced by other events in their past light cone. But in a theory of quantum gravity, where spacetime itself is subject to quantum fluctuations, this rigid causal structure may become fuzzy or even non-existent at the Planck scale. This has led to the exploration of non-local and acausal theories. Theories where distant points in spacetime can be connected in ways that defy our normal understanding. One of the most interesting and well-developed of these is the Leawick model, a type of quantum field theory that introduces new heavy particles with a peculiar property. They have a wrong sign propagator, which effectively means they can travel backwards in time for very short distances. This seemingly bizarre feature has a remarkable consequence. It can cancel out some of the problematic infinite quantities that plague standard quantum field theories, making the theory finite and more mathematically consistent. The price to pay for this mathematical elegance is a tiny, microscopic violation of causality. These violations are confined to the Planck scale and are too small to be observed in any macroscopic experiment. So they do not lead to the familiar paradoxes of time travel, but they do suggest that at the most fundamental level, the strict linear arrow of time may not hold. The universe may have a built-in microscopic acausality that is an essential part of its structure. The study of gravitational scattering at very high energies near the Planck scale has also provided hints of non-local and acausal effects. When we try to calculate the probability of two gravitons scattering off each other at these extreme energies using our standard techniques, we run into problems with unitarity, the principle that probabilities must always add up to 1. However, by using a technique called resumation, where we take into account an infinite series of quantum loop corrections, it is possible to restore unitarity. But this comes at a cost. The resumed graviton propagator, the mathematical object that describes the propagation of a graviton, develops new, complex poles. These poles do not correspond to normal, stable particles. They represent short-lived, unstable resonances, which have been interpreted as the quantum precursors of microscopic black holes. These quantum black holes are not the classical objects of general relativity. They are fuzzy, quantum states that have some of the properties of a black hole, but are not described by a classical singularity or event horizon. And one of their most striking features is that they seem to introduce a degree of non-locality and a causality into the theory. This is perhaps not surprising. A black hole, even a classical one, is a fundamentally non-local object. Its event horizon is a global property of the spacetime. The fact that the quantum precursors of black holes seem to be tied to a microscopic violation of causality is a deep and tantalizing clue. It suggests that the resolution of the conflict between gravity and quantum mechanics may require us to abandon one of our most deeply held intuitions, the idea of a strict, linear, and unbreakable chain of cause and effect. This has led to the development of two related concepts, self-healing and classicalization. Self-healing is the idea that the theory of quantum gravity has a built-in mechanism to prevent the formation of true, problematic singularities. As we approach the Planck scale, the quantum black hole resonances become the dominant effect, effectively healing the spacetime and preventing it from becoming infinitely curved. Classicalization is the idea that as we go to higher and higher energies, the quantum black hole states become more and more numerous and begin to behave more and more like a classical macroscopic black hole. The system, in a sense, classicalizes itself. In this picture, there is a minimal length in nature, on the order of the Planck length, below which it is impossible to probe. Any attempt to do so, by using higher and higher energy probes, will simply result in the creation of a larger and larger black hole, which actually hides, rather than reveals, the short-distance structure of spacetime. This is a profound and beautiful picture. It suggests that the universe has a built-in, self-regulating mechanism that protects itself from the paradoxes and infinities that have plagued our theories. It suggests that the final theory may be one that is not just mathematically consistent, but is also, in a deep sense, self-healing. The rich and varied zoo of black holes predicted by our theories, the spinning, the charged, the higher dimensional, provides a vast theoretical laboratory for exploring the intricate interplay between gravity, space-time, and the quantum world. The simplest black hole, the non-rotating, uncharged Schwarzschild black hole, is an object of perfect spherical symmetry. But the moment a black hole acquires spin, its character changes dramatically. A Kerr black hole, as it is called, is no longer a simple, static object. Its rotation drags the very fabric of space-time around with it. A phenomenon known as frame dragging. Near the event horizon, this effect is so powerful that it creates a region called the ergosphere, a place where nothing can stand still. Every object, every particle, every beam of light is forced to co-rotate with the black hole. This rotational energy can, in principle, be extracted, a process known as the Penrose process. A particle can enter the ergosphere, split into two, with one piece falling into the black hole and the other escaping with more energy than the original particle had. A spinning black hole can act as a colossal cosmic flywheel, a vast reservoir of rotational energy that can be tapped to power some of the most energetic phenomena in the universe, like the relativistic jets of quasars. The quantum world adds another layer of complexity and wonder. The process of superradiance suggests that a spinning black hole can spontaneously amplify certain quantum fields, creating a black hole bomb that would release its energy in a massive burst. The interaction between the spin of the black hole and the quantum fluctuations of the vacuum is a rich and largely unexplored area of theoretical physics. The addition of electric charge creates a Reissner-Nordstrom black hole, an object with both a gravitational and an electric field. The interplay between these two fundamental forces creates a complex and fascinating structure, with both an outer and an inner event horizon. Classically, it would be possible to travel through the outer horizon and avoid the central singularity, potentially passing through a wormhole into another region of space-time, or even another universe. However, it is thought that these inner horizons are fundamentally unstable, and that any small perturbation would cause them to collapse into a singularity. The quantum effects in a charged black hole are also intriguing. The strong electric field near the event horizon could spontaneously create real electron-positron pairs from the vacuum, a process known as the Schwinger effect, which would act to neutralize the black hole's charge. The study of these more exotic black holes is not just a mathematical exercise. It is a way of probing the deep structure of our physical theories. The existence of solutions with naked singularities not hidden behind an event horizon in some of these models, has led to the formulation of the cosmic censorship conjecture, the idea that nature abhors a naked singularity, and that some, as yet undiscovered, principle of physics must prevent their formation. The world of higher dimensional black holes, predicted by string theory, is even stranger. A black hole in 5 dimensions is not a sphere, but a black ring, and in higher dimensions, a whole zoo of black branes, black strings, and other exotic topologies become possible. The study of these objects is providing deep insights into the mathematical structure of string theory and the nature of quantum gravity. And finally, the development of black hole analogs in the laboratory is allowing us to test some of these exotic ideas experimentally by creating systems in condensed matter physics, like a Bose-Einstein condensate or a flowing fluid, that mimic the properties of a black hole's event horizon. Scientists can study the analog of Hawking radiation and other quantum effects in a controlled laboratory setting. These are not real black holes, but they are governed by similar mathematical equations, and they provide a powerful tool for testing the conceptual framework of black hole thermodynamics and the quantum physics of curved spacetime. The study of black holes, in all their varied and wonderful forms, is one of the most exciting and dynamic frontiers in modern science. They are the ultimate cosmic laboratory, a place where the laws of nature are pushed to their absolute limits and where the deepest secrets of gravity, of space-time, and of the quantum universe are waiting to be revealed. The discovery of Hawking radiation in 1974 was a moment of profound and revolutionary insight, a theoretical breakthrough that forever changed our understanding of black holes and forged a deep and unexpected link between the disparate worlds of general relativity, quantum mechanics, and thermodynamics. Until that point, black holes were seen as the ultimate cosmic prisons, perfect absorbers that swallowed everything, including light, and from which nothing could ever escape. They were thought to be completely black, completely cold, and, in a sense, completely dead. Hawking's brilliant and subtle calculation turned this picture on its head. He showed that when the principles of quantum field theory are applied in the curved spacetime around a black hole, something remarkable happens. The quantum vacuum, which we now understand to be a seething sea of virtual particle-antiparticle pairs, is disturbed by the intense gravity near the event horizon. This can lead to a process where one member of a virtual pair falls into the black hole, while the other escapes to infinity. To an outside observer, it appears as if the black hole is emitting a steady stream of particles. The particle that fell in must have a negative energy to conserve the total energy of the system, which means that the black hole loses a tiny amount of its mass energy with each emitted particle. The black hole is not black, it radiates. And this radiation, the Hawking radiation, has a perfect thermal blackbody spectrum with a temperature that is inversely proportional to the black hole's mass. This means that smaller black holes are hotter and radiate more intensely than larger ones. For a macroscopic stellar mass black hole, this temperature is incredibly, almost unmeasurably, low, a tiny fraction of a degree above absolute zero. But for a microscopic primordial black hole, the temperature could be immense. This process of radiation means that black holes are not eternal. They evaporate. As a black hole radiates, it loses mass, which causes its temperature to increase, which in turn causes it to radiate even faster. This creates a runaway process that accelerates over time, culminating in a final, explosive burst of high-energy radiation as the black hole disappears completely. This discovery had a profound impact on the field of physics, as it provided the first concrete example of a physical process that requires a combination of all three of the great theories of the 20th century. It is a phenomenon that is fundamentally gravitational, fundamentally quantum, and fundamentally thermodynamic. This led to the development of the field of black hole thermodynamics, a beautiful and consistent mathematical framework that shows a deep and surprising analogy between the laws of black hole mechanics and the laws of classical thermodynamics. The first law of black hole mechanics, which relates changes in a black hole's mass to changes in its area, spin, and charge, is the direct analog of the first law of thermodynamics, the conservation of energy. The second law of black hole mechanics, Hawking's area theorem, which states that the surface area of a black hole's event horizon can never decrease in a classical process, is the analog of the second law of thermodynamics, the law of increasing entropy. In fact, the physicist Jacob Bekenstein had proposed, even before Hawking's discovery, that the area of a black hole's event horizon is a measure of its entropy, its hidden information content. Hawking's discovery of thermal radiation provided the missing piece of the puzzle, the temperature, which allowed for a complete and consistent thermodynamic description. The third law of thermodynamics, which states that it is impossible to reach absolute zero temperature, has its black hole analog in the statement that it is impossible to create a black hole with a zero surface gravity, an extremal black hole. The discovery of Hawking radiation was a moment of stunning unification, a glimpse of the deep and beautiful connections that lie at the heart of our physical theories. But it also, as we have seen, opened up a Pandora's box of new and profound puzzles, most notably the information paradox, a puzzle that has driven much of the progress in theoretical physics for the past 50 years, and one that continues to challenge and inspire us in our quest for a final, unified theory of everything. The black hole information paradox, born from the clash between Hawking's discovery of thermal radiation and the fundamental principles of quantum mechanics, is one of the deepest and most consequential puzzles in all of theoretical physics. It is a paradox that has forced us to question our most basic assumptions about the nature of information, of space-time, and of reality itself. The core of the paradox is a stark contradiction. Quantum mechanics, at its very foundation, is built on the principle of unitarity, the idea that information is never truly lost. The wave function of a closed system evolves in a perfectly deterministic and reversible way. If you know the state of the system at one time, you can, in principle, calculate its state at any other time, either in the future or in the past. Information is scrambled, not destroyed. General relativity, on the other hand, seems to tell a different story. The event horizon of a black hole is a one-way membrane. Information can fall in, but it can never get out. And when the black hole completely evaporates into a seemingly random thermal bath of Hawking radiation, the information about the matter that formed it appears to be gone forever, erased from the universe in a way that fundamentally violates the principle of unitarity. This is the paradox. For decades, this was a battle between the two giants of 20th century physics. On one side, you had the quantum purists, who insisted that unitarity must be preserved at all costs, even if it meant that our understanding of space-time and causality had to be radically altered. On the other side, you had the relativists, including, for a long time, Stephen Hawking himself, who argued that the information was truly and irretrievably lost, and that quantum mechanics would have to be modified to accommodate this new gravity-induced non-unitarity. The debate has been long, technical, and often acrimonious. But over the years, the consensus has slowly shifted in favor of information preservation. The theoretical evidence from string theory and the ADS-CFT correspondence has provided powerful, if indirect, arguments that the process of black hole evaporation must be unitary. This has led to a host of creative and often bizarre proposed solutions to the paradox. One of the earliest ideas was that of black hole remnants. Perhaps the black hole does not evaporate completely. Perhaps it leaves behind a tiny, stable, Planck mass relic that contains all the information that fell in. This would preserve unitarity. But it comes with its own set of problems. An infinite amount of information would have to be stored in a tiny, finite object, and the universe would be filled with these otherwise undetectable relics, which would have profound cosmological consequences. Another, more mainstream, idea is that the information is not lost, but is subtly encoded in the outgoing Hawking radiation. The radiation is not perfectly thermal, but contains tiny, almost imperceptible quantum correlations that carry the information about the black hole's history. This is the most conservative and, for many, the most plausible solution. The problem is that it is incredibly difficult to show how this information encoding would work in detail. It seems to require a form of spooky, non-local interaction at the event horizon, a violation of the classical, local picture of spacetime. This has led to some of the most radical and controversial ideas in modern physics. The concept of black hole complementarity, proposed by Leonard Susskind and others, suggests that the information is both inside the black hole and outside, encoded in the radiation, but that no single observer can ever see both at the same time, thus avoiding a logical contradiction. More recently, the firewall paradox, posed by a group of physicists in 2012, has argued that the assumptions of complementarity are inconsistent, and that an observer falling into an old black hole would be incinerated by a firewall of high-energy particles at the event horizon. This would preserve unitarity, but at the cost of violating one of the most cherished principles of general relativity, the equivalence principle, which states that the laws of physics should be the same for all observers, including one in free fall. The information paradox is still far from being resolved. It is a deep and complex problem that touches on the very foundations of our understanding of the universe, but it is also a powerful and productive one. It has been a crucible for new ideas, a testing ground for our theories of quantum gravity, and a constant reminder that the universe, at its most fundamental level, is far stranger, more subtle, and more beautifully interconnected than our classical intuition can ever hope to comprehend. The answer, when it finally comes, will likely involve a radical rethinking of our concepts of space-time, of locality, and of information itself. The strange and wonderful phenomenon of quantum entanglement, the spooky action at a distance that so vexed Einstein, has, in recent years, emerged as a central and surprisingly powerful player in the ongoing drama of the black hole information paradox. It is an idea that suggests that the deep non-local connections of the quantum world may be the key to understanding the deep gravitational mysteries of black holes. The connection is a natural one. The process of Hawking radiation itself is fundamentally an entanglement phenomenon. The virtual particle-antiparticle pair created at the event horizon is an entangled system. When one particle falls in and the other escapes, the escaping particle remains entangled with its partner inside the black hole. As the black hole continues to radiate, it becomes more and more entangled with the radiation that it has emitted. This is the source of the information paradox. The principle of monogamy of entanglement in quantum mechanics states that a quantum system can only be maximally entangled with one other system at a time. The outgoing Hawking radiation particle is already maximally entangled with its partner inside the black hole. But for the information to get out, it must also become entangled with the radiation that was emitted earlier. This is a quantum impossibility, a logical contradiction that lies at the heart of the firewall paradox. This has led to a revolutionary and beautiful idea, the ER-EPR conjecture. This conjecture, proposed by physicists Juan Maldacena and Leonard Susskind, suggests a deep and unexpected equivalence between two of Einstein's most famous and seemingly unrelated ideas. EPR refers to the Einstein-Podolsky-Rosen paradox, the thought experiment that first highlighted the strange, non-local nature of quantum entanglement. ER refers to the Einstein-Rosen bridge, the original name for what we now call a wormhole, a theoretical tunnel through spacetime that could connect two distant points. The ER-EPR conjecture proposes that these two concepts are, in fact, two different descriptions of the same, underlying physical reality. A pair of entangled particles is, in a deep, geometrical sense, connected by a wormhole. The spooky, non-local correlation of entanglement is the quantum manifestation of this hidden geometrical connection. This is a staggering idea, one that weaves together the fundamental principles of quantum mechanics and general relativity in a new and profound way. It suggests that the very fabric of spacetime may be emergent from the web of quantum entanglement, and it has profound implications for the information paradox. In the ER-EPR picture, the inside of the black hole is not a separate, causally disconnected region. It is geometrically connected to the outgoing Hawking radiation via a vast and complex network of microscopic wormholes. The information is not trapped inside, it is non-locally present in the radiation outside. Through these entangled wormhole connections, the interior of the black hole is, in a sense, built from the same quantum degrees of freedom that make up the radiation. This is a concept that is deeply tied to the holographic principle. It provides a specific, dynamical mechanism for how the information in the three-dimensional bulk of the black hole can be encoded in the two-dimensional boundary of the outgoing radiation. It is a picture that is still being developed, and it is full of technical and conceptual challenges. But it is one of the most exciting and promising ideas in modern theoretical physics. It suggests that the solution to the information paradox will not be found in a small modification to our existing theories, but in a complete and radical rethinking of the relationship between quantum mechanics and the geometry of spacetime. It is a vision where the strange, non-local connections of the quantum world are not just a bizarre feature of reality, but are the very threads from which the fabric of spacetime itself is woven. Entanglement is not just a spooky action at a distance, it may be the very glue that holds the cosmos together. The cosmic stage is not just set by the familiar actors of matter and energy that we can see and touch. The vast majority of the universe's inventory, about 95% of its total mass energy content, is made up of two mysterious and invisible entities, dark matter and dark energy. And in a surprising and controversial new development, some scientists have proposed a deep and unexpected connection between these two great cosmic mysteries. A connection that is mediated by the universe's most enigmatic objects, black holes. Dark matter is the invisible scaffolding of the cosmos. It is a mysterious, non-luminous substance that does not interact with light, but whose gravitational influence we can see everywhere. It is what holds galaxies together, preventing them from flying apart. It is what shapes the large-scale structure of the universe, the vast cosmic web of filaments and voids. We know it is there, but we do not know what it is. It is likely a new, undiscovered type of fundamental particle, one that interacts only weakly with the particles of the standard model. Dark energy, as we have seen, is the even more mysterious force that is driving the accelerating expansion of the universe. It is a smooth, uniform energy that seems to be an intrinsic property of space itself, a form of cosmic anti-gravity. For a long time, these two dark components of the universe were thought to be completely separate and unrelated phenomena, but a recent and provocative theory has proposed a startling connection. The theory, developed by a team of astrophysicists, including Duncan Farah, suggests that black holes themselves could be the source of dark energy. This idea has its roots in a concept from the 1960s, which proposed that a hypothetical object made of pure vacuum energy would, from the outside, look and behave gravitationally just like a black hole. But instead of having a singularity at its center, it would be a smooth, non-singular object, its repulsive vacuum energy balanced by its own gravitational pull. The new theory takes this idea a step further. It proposes that black holes are not just made of collapsed matter, but are coupled to the expansion of the universe itself. They contain a core of vacuum energy, and as the universe expands, this vacuum energy core also grows, causing the mass of the black hole to increase over time. This is a radical idea. It means that the mass of a black hole is not just determined by what it eats, but also by the evolution of the cosmos as a whole. This is a testable prediction. If black holes are growing in this way, then the supermassive black holes at the centers of galaxies should be more massive relative to their host galaxies in the present-day universe than they were in the early universe. And this is exactly what the proponents of the theory claim to have found. By comparing the masses of supermassive black holes in distant, dormant, elliptical galaxies with those in nearby similar galaxies, they found that the nearby black holes are significantly more massive by a factor of 7 to 20 than their distant counterparts. This suggests that the black holes have been growing over cosmic time, not by eating, but by cosmological coupling. This is a highly controversial result, and it is still being debated in the astronomical community. Many other astrophysicists argue that this apparent growth can be explained by other, more conventional, astrophysical processes, such as the selection bias in the samples of galaxies being studied, or the complex and not fully understood history of galactic mergers. But if the result holds up to further scrutiny, its implications would be profound. It would mean that dark energy is not a smooth, uniformly distributed field, but is localized within the hearts of black holes. It would provide a direct physical source for the cosmic acceleration, and it would forge a deep and unexpected link between the two greatest mysteries of modern cosmology. It is an idea that is still in its infancy, and it faces many theoretical and observational challenges. For example, the total mass of all the black holes in the universe is still far too small to account for the observed amount of dark energy. But it is a beautiful and creative idea, one that is forcing us to rethink our most basic assumptions about the nature of black holes, of dark energy, and of the intricate and beautiful connections that bind our universe together. The study of black holes, in all their varied and wonderful forms, is one of the most vibrant and exciting frontiers in modern science. It is a field where the deepest questions of fundamental physics meet the most advanced observational technologies, a place where we can probe the very limits of our understanding of gravity, of spacetime, and of the quantum universe. From the classical, macroscopic black holes born from the death of massive stars to the hypothetical, microscopic quantum black holes that could be created in our particle accelerators. These enigmatic objects are a rich and fertile ground for discovery. The classical view of a black hole as a simple, featureless object, described only by its mass, charge, and spin, has given way to a much more nuanced and complex quantum picture. We now understand that black holes have a temperature, an entropy, and that they radiate and evaporate over immense timescales. This has led to the profound information paradox, a puzzle that has been a driving force in theoretical physics for half a century and has led to some of our deepest insights into the nature of quantum gravity, including the holographic principle and the ERR-EPR conjecture. The study of the different flavors of black holes, the spinning Kerr black holes with their frame-dragging ergospheres, The charged Reissner-Nordstrom black holes with their complex, multi-horizon structure. The exotic, higher-dimensional black strings and black branes of string theory is constantly pushing the boundaries of our theoretical understanding and providing new windows into the mathematical structure of the universe. And the development of black hole analogs in the laboratory, systems that mimic the properties of event horizons in controlled, condensed matter settings, is allowing us to test some of the most fundamental predictions of black hole physics, like Hawking radiation. In an experimental setting for the very first time, the recent and highly speculative proposal that black holes could be the source of dark energy is a testament to the enduring power of these objects to inspire new and creative thinking. It is an idea that, while still unproven, has the potential to unify two of the greatest mysteries in cosmology and to fundamentally change our picture of the universe's evolution. The future of black hole research is bright. With a new generation of gravitational wave detectors, like LISA, we will be able to hear the mergers of supermassive black holes across the cosmos, providing an unprecedented probe of the dynamics of spacetime in the strong field regime. With powerful new telescopes, like the James Webb Space Telescope and the Event Horizon Telescope, we will be able to see the environment around black holes with ever-increasing resolution, testing the predictions of general relativity and searching for the subtle signatures of new physics. And with more powerful particle accelerators, we may one day even create a microscopic black hole in the laboratory, opening up a direct experimental window into the world of quantum gravity and extra dimensions. Black holes are no longer just the stuff of science fiction. They are real, physical objects, and they are one of the most powerful tools we have in our ongoing quest to understand the deepest secrets of the universe. They are the ultimate cosmic laboratory, a place where the familiar laws of our world are pushed to their breaking point, and where the new, more profound, and more beautiful laws of a final, unified theory may be waiting to be discovered.